Imagine a galaxy so massive it stretches 6 million light-years across, a giant that has swallowed thousands of galaxies and trapped over 1 trillion stars in its golden glow. Astronomers call it IC 1101, but its nickname is far more haunting: the Galaxy Eater. This isn't science fiction. It's the largest galaxy we've ever found, a cosmic empire where spirals vanish, black holes collide, and entire histories are erased. Tonight, we're diving into the monster at the heart of the universe, the titan that grew by devouring the past and now sits in silence, too big to ever grow again. Discovery of the Titan. Before scientists had space telescopes or supercomputers, they used paper charts, metal telescopes, and their own eyes to make maps of the night sky. At the end of the 1800s, William Herschel had just found Uranus. This was the start of a new age of systematic scans of the sky. The plan was easy: look up at the stars, write down every weak spot, and try to figure out what the universe is all about. However, no one knew that deep within those maps lay the faint outline of something huge, something so huge that it would become known as one of the biggest monsters in the universe. IC 1101. Back then, galaxies weren't even called galaxies. They were nebulae, small fuzzy patches of light that didn't resolve into stars even under powerful telescopes. Herschel and his successors logged them by the hundreds. In 1790, records showed that the region of sky we now know as the constellation Virgo was carefully examined. Among the faint, misty objects, one was noted that looked unremarkable: a small, elongated haze barely visible. It was written down, given a number, and forgotten by most observers for nearly a century. The real breakthrough came in the late 1800s with the rise of photographic plates. Unlike human eyes, glass plates could gather light for hours, stacking photons until objects invisible to the naked eye appeared as crisp smudges of ink on black and white negatives. In 1895, astronomers using this technology revisited Herschel's nebula. It wasn't just a blur, it was enormous. The faint edges of the object extended far beyond what earlier telescopes could reveal. When the Index Catalogue IC, a supplement to the new General Catalogue of Nebulae and Clusters of Stars, was published in 1895, the object was officially christened the IC. Even then, no one realized what they were looking at. The word galaxy wasn't firmly established until Edwin Hubble's discoveries in the 1920s proved that these nebulae were vast island universes far beyond the Milky Way. The IC, catalogued decades earlier, suddenly wasn't just a smudge in Virgo, it was a galaxy, an unimaginably large one. The first hints of its true scale came in the mid-20th century, when larger observatories like Mount Wilson and Palomar aimed their giant mirrors at it. Spectroscopic studies revealed that the IC's light was redshifted, meaning it lay far beyond the Virgo cluster. Its actual home turned out to be the Abell 2029 cluster, a dense swarm of galaxies located over 1 billion light-years away. That distance alone was staggering for astronomers of the time, but the real shock came when they tried to measure its size. Most galaxies in surveys fit neatly into categories: spirals like the Milky Way, about 100,000 light-years wide, or ellipticals that might stretch a few 100,000 light-years. The IC blew those numbers apart. Estimates suggested its faint stellar halo extended millions of light-years. Later measurements refined this to nearly 6 million light-years across, so large that if it replaced the Milky Way, it would swallow not only our galaxy, but also Andromeda, Triangulum, and every smaller system in the local group, with room to spare. For decades, the IC was so faintly understood that it rarely appeared in popular astronomy books. Unlike dramatic spirals with bright arms and colorful star nurseries, the IC looked like a dull, yellowish smear in telescope images. But astronomers who studied it realized this was no ordinary smear. Its faintness was misleading. It wasn't small or weak. It was simply so far away that even its trillion stars looked like a pale blur. In the 1990s, with the advent of more powerful instruments like the Hubble Space Telescope and detailed ground-based surveys, the IC began to gain recognition as one of the largest known galaxies in the universe. Researchers measured its luminosity, counted its globular clusters, and mapped the faint halo of stars stretching out into the cluster. Every piece of data confirmed the same picture. This was a titan, a galaxy so outsized that it dwarfed everything else we had seen. The Abell 2029 cluster. If the IC is like a king, then the Abell 2029 cluster is like its crown. It is a city of galaxies that are very close together and are held together by gravity. Picture thousands of galaxies squished together in a pool of dark matter, hot plasma, and gravity wells that you can't see. The IC is the center of this cosmic city. It is a huge object at the center of the cluster that pulls everything else around it like a gravitational ruler. Abell 2029 takes its name from George O. Abell, the American astronomer who compiled one of the most comprehensive catalogs of galaxy clusters in the 1950s. Using photographic plates from the Palomar Observatory Sky Survey, Abell painstakingly identified clusters across the northern sky, ranking them by richness, the number of galaxies within them, and their distances. Abell 2029, with its tightly packed galaxies and extreme brightness, immediately stood out. It doesn't look like chaos at first glance. Abell 2029 is very laid back, unlike some groups that are rough and have people spread out. By now, its galaxies, dark matter, and hot gas have had billions of years to form a roughly circular uniform shape. The galaxy's X-ray glow is smooth and centered, and the way the galaxies are spread out makes nice spiral patterns. That is, this cluster isn't a mess of new mergers, it's a grown, stable giant, and right in the middle of it, like a rock dropped into the bowl's deepest part, is the IC. Clusters like Abell 2029 are more than collections of galaxies. They are vast ecosystems. The intracluster medium, superheated gas reaching tens of millions of degrees, fills the space between galaxies. This plasma shines in X-rays, and observations with telescopes like Chandra have revealed Abell 2029's gas to be among the brightest in the sky. Yet despite its glow, the gas is too hot to cool and condense into stars. It sits there, a silent ocean, slowly feeding the IC's growth as smaller galaxies plunge in and are stripped of their stars and gas. It's hard to believe how big Abell 2029 is. It's thought to have more than 500 trillion times the mass of the Sun, with dark matter making up most of that mass. The galaxies that we can see, like the IC, are only the tip of the iceberg. The cluster is like a huge hidden web. The galaxies are the threads, the stars are the dust, and dark matter is the net that holds it all together. Abell 2029 would break apart in a cosmic second without dark matter's glue-like pull. What makes this cluster special is how cleanly it demonstrates the link between galaxy clusters and their central giants. In many other clusters, the central galaxy is large, but not always overwhelming. In Abell 2029, the IC dominates so thoroughly that it overshadows nearly every other member. It's not just the biggest in the neighborhood, it's the neighborhood itself. The stars stripped from smaller galaxies end up swelling its already enormous halo, making it the unchallenged overlord of the cluster. Astronomers often call these central systems brightest cluster galaxies, BCGs. They are unique creatures, shaped by repeated collisions and by the gravitational collapse of the cluster as a whole. Abell 2029 is one of the clearest examples of a BCG-dominated cluster. When you measure the light, the IC accounts for a staggering fraction of the cluster's total starlight, leaving the rest of the members as supporting cast. But Abell 2029 isn't just a pretty depiction of how the galaxy is put together. It's also a space lab. Celestial scientists use it to study how dark matter, hot gas, and galaxies interact in an adult setting because it's not too far away. Its X-ray glow is smooth, which helps limit how groups change over time. Researchers can measure the dark matter halo's weight by watching how the galaxies inside it move around like test particles, and the IC itself gives us hints about how galaxies can get so incredibly big without breaking apart. New research using the Sloan Digital Sky Survey and Chandra has shown something strange. The middle part of the cluster doesn't have as many stars as theories say it should. It's like the IC has cleaned its own heart. Some ideas say that stars were thrown out by repeated supermassive black hole outbursts, or by gravitational forces acting during past merging. No matter what caused Abell 2029, it serves as a warning that clusters are not still places. They are violent places where gravity moves matter around on unthinkable scales. You couldn't stand inside the cluster because the gas inside is so hot it could melt whole solar systems. If you could, you'd see galaxies instead of stars in the sky. There were tens of thousands of them squished together, and their faint spots lit up against the background of nothingness. It would be the IC, a golden smudge in the middle that would be the brightest and look like a continent of light. Every other galaxy would look like it was being chased by a hungry animal, and it would eventually be torn apart and swallowed by Titan's endless body. 6 million light-years across. A lot of the time, science numbers are big. Ages are given in billions of years, masses are given in billions of suns, and distances are given in light-years. But once in a while, a number comes along that even trained scientists can't believe. That number is 6 million light-years for the IC. That's how far out this galaxy's star ring goes, more than 60 times the size of the Milky Way. To put that into perspective, imagine placing the IC where the Milky Way currently sits. Its edges would extend far beyond the Andromeda galaxy, far beyond the Triangulum galaxy, and even past the faint dwarf galaxies at the edge of our local group. Every major galaxy within 3 million light-years of us would be engulfed inside its borders, swallowed whole by a single system. But how do astronomers measure something so faint and so far away? The trick lies in surface brightness profiles. Every galaxy has a light distribution, bright in the center, fading at the edges. For most galaxies, that fade happens relatively quickly. But for the IC, the faint halo of stars continues and continues, so faint that only deep photographic exposures can detect it. Observatories like Hubble and advanced ground-based telescopes use sensitive detectors to stack light for hours, pulling out the wispy glow of stars that would otherwise be invisible. The result is a galaxy that doesn't seem to end, its outer halo fading so gradually into intergalactic space that it's difficult to know where the galaxy stops and the cluster begins. This enormous size isn't just a curiosity, it's a clue. Galaxies don't get this big by forming stars in place. The Milky Way is 100,000 light-years across because its gas collapsed into a disk and made stars over billions of years. The IC, on the other hand, is 6 million light-years wide because it grew by cannibalism. Every time a smaller galaxy fell into Abell 2029's center, tidal forces tore it apart. Its stars were scattered into the IC's halo, gradually building the giant's light outwards. The faint, ghostly stars at the edge of the IC are cosmic refugees, the shredded remains of galaxies that once had their own shapes, star clusters, and maybe even planetary systems. One interesting thing about how big the IC is that most of its stars are not arranged in a neat ring or circle. They're in a big cloud that's moving in all different directions. If you were on a planet on the edge of the IC, the sky would not be as full of stars as it is in the Milky Way. Instead, there would not be many stars around you. The ones that were there would be faint and stand out against the black. If you look at the galaxy by galaxy, it is both one of the biggest and one of the emptiest. The 6 million light-year figure is also controversial. Different studies measure slightly different sizes, depending on how faint a surface brightness level they use to define the edge. Some astronomers argue that the IC's size may be overstated since its halo blends into the light of the cluster. Others counter that this is precisely what makes it so extreme. Its boundaries aren't neat because it has swallowed so many neighbors. In that sense, the debate isn't about whether it's big, but whether there even is a clean way to say where the IC ends. Comparisons make the numbers even more staggering. The Milky Way, 100,000 light-years across. Andromeda, 220,000. Even the giant elliptical M87, home of the first black hole ever imaged, is only about 1 million light-years across when its halo is included. The IC dwarfs them all. It isn't just another step up the ladder, it's a whole different category, a galaxy so swollen with the remains of others that it looks more like a cluster disguised as a single system. You can also think of its size in terms of how far it goes. It would take light, which is the speediest thing in the world, 6 million years to go from one end of the IC to the other. On the other hand, light only needs 2 seconds to travel from Earth to the Moon and 8 minutes to travel from the Sun to Earth. It takes 100,000 years for light to cross the Milky Way. The IC is so big that a single photon could travel across it in the time it takes for an era of Earth's past to end. New models of galaxy growth show that galaxies this big are the last stage of galaxy development. When an area of space is millions of light years across, it stops having enough new gas to make stars. Its growth comes mostly from diels, which make its halo bigger and bigger with each meal. A cosmic giant more impressive in size than in vitality, the IC has been eating its neighbors for billions of years, which has made it swollen, slow spinning, and faint at the edges. A trillion-star home. People often use stars to talk about galaxies. There are between 200 and 400 billion stars in the Milky Way, which is where we live. Before you hear the IC, that sounds like a lot. Astronomers think that this galaxy has at least 1 trillion stars, and maybe even 2 trillion. To put it simply, the IC has more stars in it than all of the Milky Ways put together. It's hard to visualize what 1 trillion really means. If you counted 1 star per second, it would take you more than 30,000 years just to finish. And that's only if you were counting the IC's stars non-stop, day and night. The galaxy's sheer stellar population makes it one of the most luminous single structures in the observable universe, radiating across hundreds of millions of light years. But what kind of stars live inside such a giant? Surprisingly, most of them are old and faint. Elliptical galaxies like the IC are sometimes called red and dead because they no longer produce many new stars. Instead, they are filled with ancient, long-lived red dwarfs and yellow stars that formed billions of years ago, when the galaxy was still young and gas-rich. That means the IC's trillion stars are not the hot blue massive stars you see lighting up spiral galaxies, but rather a massive population of elderly suns quietly burning through their fuel. This doesn't mean the galaxy is boring. Quite the opposite. Its size and stellar content tell a story of relentless growth. The only way to build a trillion-star home is through mergers on an epic scale. Every time the IC devoured another galaxy in the Abell 2029 cluster, it added not just light but lives, tens of billions of stars torn from their homes and scattered into its halo. In fact, simulations suggest the IC has consumed thousands of galaxies the size of the Milky Way over its history. That's why its population is so staggering. What's even more amazing is how evenly these stars are spread out. If a system was formed by so many violent crashes, it might appear disorganized, with stars that aren't all the same brightness and groups of stars that show where old galaxies used to be. Of course, the IC's body is very similar. It slowly loses brightness from the middle to the ends, and there are no clear scars. That smoothness hides a rough past, like the smooth stones of a stream that have been through many crashes and floods. Within this trillion-star population lie hundreds of millions of globular clusters, compact swarms of stars that orbit like satellites. These clusters act as fossils, preserving the chemical fingerprints of the galaxies the IC absorbed. By studying their composition, astronomers can reconstruct the galaxy's growth history piece by piece, like detectives examining relics from an ancient civilization. Early results suggest that some of the IC's globular clusters are among the oldest known, forming more than 12 billion years ago when the universe was still young. If you could drift through the IC, the experience would be surreal. Near the core, the density of stars would be breathtaking, thousands of suns filling every corner of the sky. Farther out, the stars thin into the halo, scattered like embers drifting away from a fire. Planets may orbit some of these stars, though most would be inhospitable, bathed in the radiation of an aging stellar population. Even so, the sheer number of stars makes it statistically likely that the IC hosts untold billions of worlds, some perhaps with conditions suitable for life. Recent studies with tools like the Sloan Digital Sky Survey have found another interesting fact. Even though the IC has a lot of stars, its stellar population per unit volume is much lower than that of smaller galaxies. In other words, the stars are spread out over such a huge area that the galaxy seems almost empty. What a strange thing about the IC. It's the universe's most crowded and largest home at the same time. The yellow glow of age. Pictures of the IC don't show the bright blues of spiral arms or the pink knots of areas where stars are being formed. The galaxy shines with a soft, golden haze instead. Its light is mostly made up of yellow and red stars, which is a sign of how old it is. What is the IC? It's not a galaxy in its prime. It is old, worn out, and bright with the faint light of stars that formed billions of years ago. The color of a galaxy is more than an aesthetic detail. It's a direct clue to its history. Young galaxies burst with massive, hot stars that burn bright and blue, but live short lives, often only a few million years. As these stars die, only smaller, cooler stars remain, and the overall color shifts toward yellow and red. That's exactly what we see in the IC. A stellar population that has long since stopped being refreshed with newborn stars. Astronomers describe this process as quenching, the shutting down of star formation. In the IC's case, it likely quenched billions of years ago. With so much of its gas consumed or stripped during mergers, and with its central black hole likely blasting energy into its surroundings in the past, the galaxy simply ran out of fuel to ignite new stellar nurseries. What remains are mostly population 2 stars, old, metal-poor suns that have been burning quietly since the early universe. The term metal-poor in astronomy doesn't mean these stars lack iron skyscrapers or shiny coins. It means that they formed before the universe was enriched with heavy elements. In the first few billion years after the Big Bang, the only elements available in abundance were hydrogen and helium. Heavier elements like carbon, oxygen, and iron were forged later in the cores of stars and spread by supernovae. The IC stars, being old, contain relatively few of these elements, and that makes them burn with a steady, yellowish glow. Spectroscopic surveys of the IC's light reveal absorption lines that confirm this low metallicity. Compared with the Milky Way's disk stars, the IC's stellar population is chemically ancient, more closely resembling the halo stars of our galaxy. In other words, when we study the IC, we are looking at a fossil record of some of the earliest star generations to form in the cosmos. Its golden color also tells us about its star formation history. Most galaxies grow in fits and bursts. Mergers trigger waves of new star formation, gas cools and condenses, and stellar nurseries light up again. But the IC shows almost no signs of recent bursts. Instead, its stars formed early, in great quantities, and then the process nearly stopped. Some astronomers estimate that the majority of its stellar population is older than 10 billion years, meaning the IC became red and dead when the universe itself was still young. The uniformity of this color is striking. In spiral galaxies, the central bulge is often yellow, but the outer arms glow blue with young stars. In the IC, the entire structure, core, halo, and outskirts, shares the same washed-out hue. That uniformity is one of the key reasons it is classified as a giant elliptical galaxy. It lacks the patchwork of colors seen in spirals, because it lacks the diverse environments where stars are still being born. These words make you think of something frightening. The IC's golden light is the glow of billions of dying suns, each one slowly dying. Red dwarfs are the most common type of star in the sky. They may still have trillions of years to live, but they don't shine very brightly. Once blue-white titans, these huge yellow stars are now moving toward red giant stages, where they will swell and die. Galaxy's light isn't the sparkle of youth. It's the slow burn of an old kingdom. The yellow color also makes the IC easier to study in some ways. Blue stars can outshine their surroundings, hiding faint features. But the IC's smooth golden glow allows astronomers to trace its surface brightness profile with unusual clarity, revealing just how far its halo extends. The faintest edges, glowing softly against the blackness of space, are made of the oldest stars, the ones stripped from other galaxies, and smeared into its outer layers over billions of years. The James Webb Space Telescope has added new detail to this picture. Recent near-infrared observations suggest that the IC's stars are not just old, but remarkably uniform in age and metallicity. Unlike the Milky Way, which shows distinct populations from different epochs and mergers, The IC looks like a finished product. It had its growth spurt early, then coasted. That makes it one of the clearest examples of a quenched giant in the universe. The ultimate elliptical galaxy. Galaxies come in a lot of different forms, including spiral galaxies full of young stars, curvy galaxies that have been messed up by collisions, and dwarf galaxies that are so dim they hardly count as galaxies at all. However, the IC is in a completely different group. Astronomers have found the biggest and most extreme example of this type of galaxy. It is a giant elliptical galaxy. The IC is like a rock of light, smooth, round, and stunning. The Milky Way is like a whirlpool of order. Elliptical galaxies are defined by what they lack. No spiral arms, no clear disk, no organized lanes of gas or dust. Instead, their stars orbit in random directions, creating a structure that looks more like a sphere or oval than a flat disk. The classification system created by Edwin Hubble in the 1920s ranks ellipticals from nearly spherical, E0, to very stretched out, E7. The IC doesn't even fit neatly into that scheme. It is so large and diffuse that its shape seems to transcend the categories, less like a galaxy, more like a glowing cosmic continent. The reason ellipticals like the IC exist comes down to mergers. When two spiral galaxies collide, their ordered disks are disrupted. Stars are thrown into random orbits, gas clouds smash together, and the neat spiral arms dissolve into chaos. Over time, the resulting galaxy relaxes into a smooth ball of stars. Repeat this process thousands of times, and you get a monster like the IC. Its elliptical shape is the fossilized scar of billions of years of cosmic violence. Unlike spirals which spin like giant pinwheels, ellipticals barely rotate at all. Their stars move in every direction, producing what astronomers call velocity dispersion. If you were inside the IC looking up, the stars wouldn't all seem to flow along one direction as they do in the Milky Way. Instead, they would move chaotically, like bees swarming in a hive. This lack of order is one reason why ellipticals appear so smooth. They are blended by randomness. What sets the IC apart is its sheer scale as an elliptical. Most ellipticals are a few 100,000 light-years across. Even the famous Messier 87 at the center of the Virgo cluster is only about 1 million light-years in diameter when you include its halo. The IC, at nearly 6 million light-years across, is in another league altogether. That size, combined with its smooth light profile, makes it the ultimate example of what ellipticals can become. Its structure also reveals important physics. In spirals, gas settles into thin disks because angular momentum forces it to flatten. In ellipticals, random motion prevents that flattening. But at the IC's size, there's almost no gas left to settle. Observations show its interstellar medium is nearly empty, stripped away by repeated collisions and heated by the cluster's hot plasma. That emptiness explains why the IC is red and dead. It has the stars, but no fuel for new ones. The IC is not just big, it's extraordinarily luminous. When astronomers measure its brightness, they find it shines with the light of trillions of suns. Yet its surface brightness, how much light you see in any given patch, is low compared to smaller galaxies. That's because its stars are spread across such a vast area. It's like smearing a campfire across a football field. The total light is immense, but the glow looks faint and even. One of the puzzles giant ellipticals pose is the so-called smoothness paradox. How can a galaxy assembled from countless messy mergers look so uniform? Simulations show that gravity is a master sculptor. Given enough time, the random motions of stars even out, smoothing away scars from past collisions. Over billions of years, the turbulence of mergers fades into a calm, featureless glow. The IC is the ultimate proof of this process. Its light profile matches theoretical models almost perfectly, even though its history must have been unimaginably chaotic. Being the ultimate elliptical also means the IC is a kind of cosmic endpoint. Spiral galaxies like the Milky Way are still alive, forming stars and maintaining their structure. But in the long run, repeated mergers transform most large galaxies into ellipticals. In dense clusters, this process is accelerated, and giants like the IC form at the centers. When astronomers look at the IC, they see the future, not just of individual galaxies, but of galaxy clusters themselves. It shows what happens when gravity has had billions of years to do its work without interruption. The black hole at the center. In the middle of every big galaxy, there is a monster. The Sagittarius A star in the Milky Way is a giant black hole that weighs as much as 4 million suns. Andromeda is even bigger, with about 100 million suns. But when we look into the IC, the numbers jump to a level that's hard to understand. At its heart is a giant black hole that probably weighs tens of billions of solar masses. It is so huge that it is much bigger than the biggest black holes we know of so far. Why do astronomers think it's so massive? The answer lies in the tight connection between galaxies and their central black holes. Observations over decades have revealed a surprising rule. The bigger the galaxy's central bulge, the bigger the black hole. This relationship, called the M-sigma relation, links the motions of stars in the galactic core to the black hole's mass. When scientists measured the velocity dispersions in the IC's central regions, the numbers pointed to an object of staggering scale, possibly as much as 40 billion solar masses. That makes it a candidate for one of the most massive black holes in the observable universe. A black hole that big doesn't just sit quietly. In the past, the IC's central engine likely blazed as an active galactic nucleus AGN, gobbling up in falling gas and unleashing radiation across the spectrum. Jets of charged particles may have speared out for hundreds of thousands of light years, lighting up the cluster like a cosmic beacon. The evidence for this activity lingers: cavities in the surrounding hot gas, faint radio emissions, and a depleted stellar core that looks scoured by gravitational upheaval. Today, the black hole seems dormant, but its fingerprints remain everywhere. To appreciate its scale, consider this: the event horizon, the point of no return, of a 40 billion solar mass black hole would be nearly 800 billion kilometers wide. That's about 5,000 times the distance between Earth and the Sun. A black hole of that size could easily swallow our entire solar system and still have room to spare. Even light would take more than 2 days to circle its edge. What's even more noteworthy is how this kind of black hole comes to be. Huge black holes start out small. This could be because the first stars collapsed, or because huge gas clouds collapsed directly in the early universe. From there, they get bigger by eating gas and combining with other black holes when galaxies crash into each other. Over billions of years, the IC has eaten many galaxies, and with each merger, it brought both stars and black holes in the center. In a spiraling motion, these smaller black holes merged and fed the center giant until it hit its current huge size. That process leaves scars. One of the mysteries of the IC is its core depletion. The central regions appear emptier than expected, as if stars have been slingshotted out. Astronomers believe this is the handiwork of the black hole. When two black holes merge, their combined gravitational dance can fling surrounding stars outward at extreme speeds, creating what's called a core-scoured profile. The depleted core of the IC suggests it has gone through this process multiple times, each one adding to the central black hole's weight while hollowing out its neighborhood. If you could hover near the edge of this black hole, not that you'd survive, you would see one of the strangest sights in the universe. Matter spiraling in would heat to millions of degrees, releasing more energy than entire galaxies. To an outside observer, time itself would appear to slow near the horizon. The stars near the center would whirl with dizzying velocities, pulled by a gravity well deeper than almost any other known. Despite its terrifying nature, the black hole is also the reason the IC is the way it is. When it was active, its jets and radiation likely quenched star formation by heating and blowing away gas. Without that feedback, the IC might have continued to grow uncontrollably, forming new stars until it became unstable. The black hole, paradoxically, acted as a kind of regulator, both a destroyer and a stabilizer of the galaxy's future. The numbers may seem abstract, but think of it this way. Every star you've ever seen in the night sky, every galaxy photographed by Hubble, every burst of light from a distant quasar. The IC's black hole outweighs them all combined, many times over. It is not just an object. It is a cosmic leviathan, an anchor that shapes the destiny of trillions of stars, and the cluster they live in. The Cannibal's Feast. The IC didn't grow to be the biggest galaxy in the universe by just staying out of the way. It turned into a monster by eating other things. Galactic cannibalism is what astronomers call it, and the IC is the most extreme case we know of. Its 6 million light-year ring is full of stars, clusters, and faint streaks of light that show that there has been a feast for billions of years. In the crowded environment of the Abell 2029 cluster, galaxies don't just pass each other politely. Gravity pulls them into dances, and those dances often end with one partner being ripped apart. Smaller galaxies lose their outer stars first, which are smeared into faint streams. Then their gas is stripped away by the cluster's hot plasma. Finally, the core itself plunges into the maw of the central giant. The victim disappears, its identity erased, its stars added to the glow of the IC. Astronomers can actually see the leftovers of these meals. Deep images reveal tidal streams, arcs and shells of stars curving around the IC. These are the skeletal remains of galaxies being torn apart right now. In simulations, such features are common whenever a giant galaxy consumes a smaller one. Over time, the streams fade and disperse, blending into the halo. That's why the IC looks smooth today. It has eaten so many galaxies that their scars have blurred into one golden haze. The scale of this feasting is hard to overstate. Some models suggest the IC has swallowed thousands of Milky Way-sized galaxies during its lifetime, plus countless dwarfs. Every one of those galaxies once had its own history. Spiral arms, star clusters, maybe even planetary systems with habitable worlds. Now they are anonymous parts of the Titan, their individuality erased by gravity's hunger. The process isn't random. The central galaxy of a cluster like Abell 2029 sits at the bottom of the cluster's gravitational well. Smaller galaxies orbit around this center, but over time, friction with the surrounding dark matter and hot gas robs them of momentum. Slowly but inevitably, they spiral inward. This mechanism, called dynamical friction, is one of the key engines of cannibalism. The more massive the central galaxy becomes, the more irresistible its pull. The IC is the ultimate example of this snowball effect. The more it eats, the more powerful its appetite becomes. Cannibalism also explains the IC's vast stellar halo. Unlike the neat disks of spirals, ellipticals are surrounded by diffuse envelopes of stars that stretch far into intergalactic space. These halos are built from shredded galaxies. As stars are stripped, they settle into extended orbits around the central giant. In the IC, that halo is the largest ever recorded, spanning millions of light years. Every faint photon in that halo is a gravestone for a galaxy consumed long ago. The violence of this process leaves other signatures too. Globular clusters, compact groups of old stars, are often captured intact. The IC contains hundreds of millions of these clusters, far more than the Milky Way's modest few hundred. Their orbits and compositions act as fossils of past mergers, allowing astronomers to reconstruct which kinds of galaxies were devoured and when. Many of the IC's globulars show chemical fingerprints of ancient origins, suggesting that cannibalism began early, when the universe itself was still young. Cannibalism also affects the growth of the central black hole. Every time the IC consumes another galaxy, it likely absorbs that galaxy's black hole as well. Over billions of years, these mergers built up the central beast to its staggering tens of billions of solar mass scale. In this way, the black hole and the galaxy's halo are two sides of the same feast, one consuming stars, the other consuming darkness itself. From our point of view, it's easy to think that cannibalism is bad. But in the grand scheme of things, it's also artistic. The IC kept the stars of galaxies by combining them instead of throwing them into space. It gave them a new place to live, even if that place is a huge, uncaring kingdom. Galaxies in groups might stay small and dim if this process doesn't happen. Their light could be lost in the bright plasma. Instead, they became a part of a system that is so big it makes us question what we can imagine. The core depletion mystery. They are still trying to figure out the puzzle that is at the center of the IC. There is something wrong with the center parts of it. The light from the galaxy doesn't peak as strongly in the middle as was thought. The core instead looks drained, which means it is less full and smooth than models would suggest. There are so few stars in the sky that it looks like the middle has been taken out. The IC shows this strange effect on a bigger scale than almost anywhere else. It's called core depletion. In most galaxies, brightness increases dramatically toward the center. The Milky Way's bulge, for example, is packed with stars orbiting close to Sagittarius A star, our supermassive black hole. But when astronomers map the IC's light profile, they find a central region hundreds of light-years wide that is dimmer than it should be. The missing stars haven't vanished. They've been pushed outward, leaving a shallow cusp where a steep spike should exist. The leading explanation involves the IC's supermassive black hole, which likely weighs tens of billions of suns. When two galaxies merge, their central black holes sink to the middle of the new galaxy. There they form a binary system, orbiting each other in a gravitational dance. As they spiral inward, their combined pull acts like a slingshot, flinging nearby stars out of the core at extreme speeds. Some stars are ejected into the outer halo. Others are accelerated so much they escape the galaxy entirely, becoming hypervelocity stars wandering intergalactic space. This process, called gravitational scouring, is thought to be the reason the IC's core looks hollowed out. And because the IC has likely experienced thousands of mergers, it may have gone through this process multiple times, each one deepening the depletion. The result is a core far larger than that of ordinary ellipticals, a yawning gap that reflects the violent history of repeated black hole pairings and mergers. Observational evidence supports this. The Hubble Space Telescope and ground-based surveys have measured the stellar density profiles of giant ellipticals, including the IC. In every case, the most massive galaxies show the most extreme core depletion. The IC's core radius is estimated at several thousand light-years, so big that our entire Milky Way would fit inside the missing region. That's not just unusual, it's record-breaking. But the mystery doesn't end there. Simulations suggest that gravitational scouring alone may not be enough to explain how empty the IC's center appears. Some researchers argue that additional processes must be at work. One possibility is AGN feedback, powerful outbursts from the central black hole that heat and expel gas, preventing stars from forming in the core. Over billions of years, this would keep the central regions underpopulated compared to the rest of the galaxy. Another theory involves repeated tidal stripping, wherein falling galaxies lose their stars before reaching the center, leaving the core underfed while the halo fattens. Whatever the mechanism, the depleted core is more than an oddity. It's a record of cosmic violence. Every star missing from the IC's center is a survivor of some catastrophic event, whether flung out by a merging black hole or prevented from ever forming in the first place. The core is like a scar, carved into the galaxy's face by a history of collisions too extreme for words. The mystery deepens when you consider the stars that were ejected. Where are they now? Some astronomers believe the IC may be surrounded by a vast population of intergalactic stars drifting freely in the cluster without belonging to any one galaxy. Observations of other clusters show faint glows of intra-cluster light thought to come from such orphaned stars. If true, then the IC's missing core stars may not be gone at all. They may simply be wandering, scattered across millions of light-years, invisible except as the faintest background glow. The depletion also ties back to the IC's identity as a brightest cluster galaxy. Other massive ellipticals in similar environments show the same effect, though rarely as extreme. It suggests a pattern. The more a galaxy grows by cannibalism, the more its core is carved out. The IC, being the largest of them all, simply displays the phenomenon on the grandest stage. An empty core might not sound very important to the average person. The light shape is just a little flatter. Astronomers, on the other hand, see it as similar to discovering fingerprints at a crime scene. It tells us that huge black holes have danced, crashed into each other, and changed the shape of the galaxy from the inside out. It's a quiet sign of huge forces at work, forces strong enough to throw stars the size of the Sun into the space between galaxies. The faint halo problem. Astronomers take long exposure pictures of the IC, And the first thing that stands out is not its bright center glow, but the ghostly light that goes out into space. This is its stellar halo, which is a thin, spread-out band of stars that surrounds the galaxy. Halos in most galaxies are pretty small, only a few 100,000 light-years across. But the IC's halo is very different. It goes on for millions of light-years, which is longer than any other halo that is known. This brings up the weak halo problem, which is one of the biggest mysteries about this huge galaxy. Halos are built through mergers. Every time the IC devoured another galaxy, some of that galaxy's stars were flung into elongated orbits, forming streams and arcs. Over billions of years, those streams blended into a diffuse glow around the central giant. For normal galaxies, this process produces a halo that is faint but measurable. For the IC, the halo is so enormous and so faint that astronomers struggle to define where it ends. The problem is not whether the IC has a halo, it's that its halo might be too large to explain with conventional models. Detecting such faint light is extremely difficult. The human eye can't see it, even through powerful telescopes. Astronomers rely on digital detectors that can gather light for many hours, stacking exposures to reveal features billions of times dimmer than the night sky. Even then, background contamination from the intracluster medium, hot gas and intracluster stars, blurs the line between what belongs to the IC and what belongs to Abell 2029 as a whole. The faint halo problem is partly a problem of definition. Is the halo truly the IC's, or is it simply the overlapping light of the entire cluster? However, there is also a physical secret. Simulations of how galaxies grow show that halos get bigger as galaxies join. However, the IC's cloud is way too big, going far beyond what even thousands of mergers should create. Some scientists think that a lot of this ring is not made up of galaxies. The IC ate directly, but it did so from stars that were stripped from galaxies that were circling the cluster and never made it to the center. To put it another way, the IC's ring could be a mix of galaxy light and light from inside the cluster. That merging makes it hard to say what a galaxy really is. The faint halo problem also reveals something about dark matter. Stars in the outer halo move in orbits that can only be explained if the IC is embedded in a massive dark matter envelope. Without dark matter's gravitational grip, those stars would drift away into space. By studying how faint halo stars move, astronomers can estimate the mass of the invisible halo. For the IC, the numbers suggest an enormous dark matter cocoon, possibly one of the largest ever measured. That halo isn't just faint light. It's a tracer of unseen mass on the grandest scale. Another problem is that halos aren't all the same. The IC's surface looks smooth, but close imaging shows weak tidal streams, which are wisps of stars that are still settling down after merging recently. The halo is still growing and taking in galaxies as shown by these ghostly lines. It's not just a static shell, it's a live record of eating people with scars that can still be seen. This movement is hard to see because the halo is so thin, making it one of the hardest but most important parts to study. There's also a paradox. The halo is full of stars, but their density is incredibly low. If you stood on a planet in the far outskirts of the IC, the night sky would be almost empty. Even though you're inside the largest galaxy known, you might see fewer stars than we do from Earth. That's because the stars are spread thin across millions of light years, their combined light barely detectable from afar. The faint halo is both vast and lonely, a contradiction that makes the IC so unusual. The James Webb Space Telescope and new ground-based surveys are beginning to shed light on this puzzle. Deep infrared images can pick out faint halo stars, even at 1 billion light-years away. Early results suggest that the IC's halo is not just unusually large, it may also be unusually structured, with shells and gradients that hint at a complex growth history. This could mean that our standard models of halo formation underestimate how extreme cannibalism can become in cluster centers. Dark matter in abundance. Astronomers can't figure out how much the IC weighs. Its trillions of stars, huge ring, and giant black hole help explain some of its size, but not nearly enough. The light we see is only a small part of the story. The rest, which makes up the vast majority of the galaxy's mass, can't be seen. Dark matter is this hidden stuff. and there is a huge amount of it in the IC. Dark matter is one of the greatest mysteries in modern astrophysics. We can't see it, touch it, or detect it directly with telescopes. Yet we know it's there because of its gravitational influence. In galaxies like the Milky Way, dark matter reveals itself through rotation curves. Stars at the edges orbit faster than expected, as if pulled by an invisible hand. In clusters like Abell 2029, dark matter's presence is even more obvious, shaping the motions of thousands of galaxies and bending the path of light itself. The IC, sitting at the center of the Abell 2029 cluster, is wrapped inside one of the largest dark matter halos ever measured. Its stars and gas together add up to several trillion times the mass of the Sun. But its dark matter halo may weigh over 10 to the 15th solar masses, about a quadrillion suns. That's not just massive, that's galaxy cluster massive. It means the IC's very identity is tied to the invisible structure around it, a vast dark matter web that forms the skeleton of the universe itself. Observations from different angles all point to this riches. First, the galaxy's star ring goes out millions of light years, which is much farther than normal matter could stay in place. Those weak outer stars would just drift off into space between galaxies if there wasn't a huge cage of dark matter around them. Next, X-ray tests of the hot gas around the IC shows that the gas is stuck in a deep well of gravity. Dark matter, a lot of it, is the only thing that can explain how it's spread out. Third, studies that use gravitational lensing, in which light from background galaxies is bent by Abell 2029, show mass densities that are much higher than what can be seen from stars. All of these hints lead to the same conclusion. The IC is an island that can be seen floating in an ocean that can't be seen. The sheer abundance of dark matter in the IC also helps explain its size. Smaller galaxies can be torn apart in collisions, but the IC's dark matter halo acts as a shield, keeping the system intact as it devours others. When two galaxies merge, their dark matter halos merge first, creating a gravitational envelope that traps stars and gas inside. The IC's halo, already massive, snowballed with every merger, expanding into one of the largest single dark matter structures we've ever inferred. And yet, the details remain puzzling. Simulations of dark matter predict that halos should have sharp central cusps, where density spikes near the core. But in the IC, the central light profile is unusually flat, suggesting that stars, and perhaps even dark matter, have been pushed outward. One possible explanation is black hole feedback. When the IC's central black hole was active, its jets may have injected so much energy into the surrounding matter that even dark matter was redistributed, softening the core. If true, the IC offers rare evidence that black holes don't just sculpt stars, they may reshape dark matter itself. A further puzzle is the weak cloud problem, which is related to the talk about dark matter. How much of the light that's spread out around the IC comes from its own cloud, and how much comes from the cluster? Some scientists say that the IC's halo is very similar to Abell 2029's dark matter distribution. This means that the galaxy is not a separate object, but rather a visible core of a structure that spans the whole cluster. Some people think that the IC is part of a dark matter ring, not just inside it. They see it as the bright tip of a gravity iceberg. If you could somehow see dark matter, the IC would look nothing like the smooth golden glow we observe. Instead, it would appear as a vast invisible bubble, millions of light years wide, dwarfing even the galaxy's luminous body. Its density would be greatest near the center, but extend far beyond the visible edges. The stars we see are just sparks embedded in this hidden framework, like fireflies in the middle of a giant glass dome. The quenching of star formation. The IC's size isn't the only thing that stands out, its silence is too. You might think that a galaxy with more than 1 trillion stars would have bright nurseries, groups of young suns and glowing clouds. It's more like the IC is almost dead when it comes to making stars. Even though it has trillions of solar masses of gas in it, almost none of that gas is making stars right now. These changes are known to astronomers as quenching, and the IC is one of the most extreme examples of a quenched galaxy that has ever been seen. So why has star formation stopped? The answer lies in the galaxy's violent past. Every time the IC merged with another galaxy, the collision stirred and heated its gas. Normally, when gas cools, it condenses into clouds that collapse under gravity to form new stars. But in the IC, much of that gas has been stripped, blown away, or heated to such high temperatures that it can no longer cool efficiently. Instead of collapsing into stars, the gas floats as hot plasma, glowing faintly in X-rays, but useless for making suns. Another culprit is the supermassive black hole at the center. When it was active, it likely unleashed powerful outflows of energy, blasting surrounding gas outward. This process, known as GN feedback, is like a galactic thermostat turned too high. It prevents gas from cooling, effectively shutting down star formation across the entire system. Evidence for this is seen in the X-ray cavities around the IC regions, where jets from the black hole once carved holes in the surrounding plasma. The energy from those outbursts could have sterilized the galaxy, cutting off its ability to grow new stars. Cluster environments also play a role. The IC sits at the center of Abell 2029, a dense swarm of galaxies embedded in hot intra-cluster gas. Any smaller galaxy that falls toward the IC is stripped of its cold gas before it even arrives. By the time it merges, it has nothing left to feed star formation. This process, called ram pressure stripping, turns once healthy spiral galaxies into gas-poor skeletons before they're consumed. The IC doesn't just eat galaxies, it eats them after the cluster has already drained them dry. What's left behind are stars that are overwhelmingly old. Most of the IC's stellar population formed more than 10 billion years ago during an early cosmic boom when gas was plentiful. After that, star formation rates plummeted. Today, astronomers estimate that the IC produces only a tiny fraction of a solar mass worth of stars each year, nearly negligible compared to the Milky Way, which still creates 1 to 2 new stars annually. For a galaxy 60 times larger than ours, that silence is staggering. Quenching doesn't mean the galaxy is entirely empty of gas. Observations with radio telescopes have detected faint signals of hydrogen spread across its halo. But this gas is diffuse and heated, unlikely to ever collapse into stars. It's like having all the ingredients for a fire scattered too thinly to ignite. The fuel is technically there, but it's unusable in its current state. Quenching is not unique to the IC. Many massive ellipticals share the same fate. In fact, astronomers now see quenching as a natural endpoint of galactic evolution. The bigger a galaxy becomes, the more violent its history, the hotter its gas, and the stronger its black hole's feedback. The IC is simply the most extreme case, a galaxy so massive, with such a turbulent past, that star formation has been almost completely erased. This lack of new stars also explains the IC's color. Without young, hot blue stars to brighten it, the galaxy glows primarily with older, cooler yellow and red stars. It is the classic red and dead elliptical, a fossil glowing with the afterlight of ancient stellar generations. The smoothness of its light profile, combined with its quenched state, paints a picture of a galaxy that did most of its growing early and has coasted ever since. But quenching doesn't just affect the IC itself, it influences its entire cluster. Without star formation, the IC no longer adds fresh radiation or heavy elements to the intracluster medium. The hot gas around it remains largely unchanged, slowly enriched only by the death of aging stars. In effect, the galaxy has entered a state of cosmic retirement, where its role is no longer to build, but simply to preserve. The AGN that once was. The IC looks calm today, with a golden haze of old stars, a faint ring that goes into darkness, and few to no new stars forming. But this galaxy might have looked very different billions of years ago. It used to have an active galactic nucleus AGN at its center, which was a cosmic signal driven by the black hole at its center's never-ending hunger. Even though the action has stopped for a long time, the proof is still there, telling stories of a giant that used to roar. AGN are some of the brightest phenomena in the universe. When gas falls toward a supermassive black hole, it doesn't plunge straight in. Instead, it spirals into an accretion disk, heating to millions of degrees. Friction and magnetic fields launch jets of charged particles that shoot out at near-light speeds, sometimes stretching across hundreds of thousands of light-years. For a time, the galaxy's center can outshine every star combined. In its prime, the IC's AGN would have turned the galaxy into a quasar-like lighthouse, visible from across the cosmos. Astronomers can't rewind the universe to watch it directly, but they can read the signs. One clue lies in the X-ray cavities around the IC, bubbles carved into the hot intracluster gas. These cavities are thought to be the scars of ancient jets, blasting outward from the central black hole and pushing gas aside. Observations of similar galaxies show that such cavities can last for hundreds of millions of years, fossilized evidence of AGN outbursts. The IC's environment shows the same marks, proof that its black hole was once ferociously active. The fact that its center is empty is another piece of proof. As was already said, the middle of the IC is strangely empty, with stars that should be there but aren't. Large black holes may have merged to explain some of this, but AGN action may have also played a part. Black holes can send out strong radiation and winds that could have heated or pushed gas out of the way before new stars could form. This makes a galaxy with a big center, and not many new stars forming. This is partly because of how angry the AGN is. Radio observations add more hints. Though the IC is quiet today, faint radio emissions have been detected around its core. These are like the afterglow of a once mighty storm, remnants of jets that no longer blaze but left behind a trace of synchrotron radiation. Combined with the X-ray cavities, they suggest that the black hole flickered on and off over time, with multiple episodes of activity punctuating the galaxy's history. The impact of such an AGN on the IC would have been enormous. For one, it likely contributed directly to the quenching of star formation. When the black hole ignited, the energy released was enough to heat surrounding gas to tens of millions of degrees, making it impossible for that gas to cool and collapse into new stars. This process, called AGN feedback, is now understood to be one of the key reasons massive galaxies stop forming stars. The IC's quiet present is a direct consequence of its noisy past. The AGN also helped shape the galaxy's environment. By injecting energy into the intracluster medium, it may have prevented the gas around Abell 2029's center from collapsing into new galaxies. In other words, the IC's black hole didn't just affect its host, it regulated the entire cluster's core, acting as a cosmic thermostat. This is why astronomers now see AGN not as side effects, but as central players in galaxy evolution. Without them, giants like the IC would look very different. But why is the IC's AGN silent now? The answer likely comes down to fuel supply. To power an AGN, a black hole needs a steady stream of gas. In the IC, most of that gas has already been consumed, expelled, or heated beyond usability. With little left to feed on, the black hole has gone dormant, leaving behind only faint echoes of its past activity. It's not dead, black holes never die, but it's sleeping, waiting for the next opportunity to awaken. If the IC were to experience another major merger with a gas-rich galaxy, its AGN could flare up again. For now, though, the galaxy's surroundings are so stripped that such an event is unlikely. The days of the IC shining as a quasar are probably over. Its legacy is written in the scars, the cavities in the gas, the quiet core, the absence of star formation. X-ray emissions from the cluster. You would be shocked if you could see the Abell 2029 cluster in X-rays instead of visible light. You would not see tiny galaxies spread out in the dark. Instead, you would see a fiery, ghostly cloud filling the space between them. Tens of millions of degrees of heat have made this glow possible. The plasma is so hot that it only shines in X-rays. The IC is right in the middle of this firestorm, surrounded by an atmosphere that is both dangerous and beautiful. Clusters of galaxies are not empty between their members. They contain enormous amounts of intracluster medium, ICM, gas stripped from galaxies during collisions, or left over from the cluster's formation. In Abell 2029, this medium is especially bright and smooth, making it one of the best-studied X-ray clusters. Observations with telescopes like Chandra and XMM Newton have revealed a glowing ball of plasma extending millions of light years, with the IC at its gravitational center. The temperatures of this gas reach over 80 million degrees Kelvin. At those extremes, atoms are stripped of their electrons, creating a soup of nuclei and free electrons. When these particles collide, they emit X-rays. To us, those photons are invisible without specialized detectors, but they carry vital information. By mapping the X-ray emissions, astronomers can trace the distribution of the gas, weigh the cluster, and probe the influence of dark matter. Abell 2029's X-ray emissions are unusually regular. Many clusters look ragged, with clumps and shocks from recent mergers. But Abell 2029 is relaxed, meaning it has settled into equilibrium over billions of years. Its X-ray glow is nearly spherical, centered perfectly on the IC. That symmetry tells astronomers that the cluster is mature and stable, an ancient giant that hasn't seen a major disruptive merger in a long time. The X-rays also reveal the fingerprints of the IC's past. In many clusters, cavities or bubbles in the X-ray glow are evidence of past AGN outbursts. In Abell 2029, faint structures suggest that the IC's central black hole once blasted jets that pushed gas aside. These cavities are like scars in the plasma, preserved long after the outbursts ended. By measuring their size and the energy required to carve them, scientists can estimate how powerful the IC's AGN must have been. The results are staggering, outbursts releasing more energy than millions of supernovae combined. When you look at the cluster's heart, you find another puzzle. In theory, the hot gas should slowly cool down and compact, letting it fall into the galaxy and help new stars form. This is known as a cooling flow, and scientists thought it would explain why the centers of galaxy groups are so heavy for a long time. But the cooling flow doesn't seem to be there in Abell 2029 or many other groups. The gas is hot, but it doesn't cool down fast enough for stars to form at the rates that were thought. The cooling flow problem is the name for this difference. The answer might be in the IC's black hole. Its past explosions put so much energy into the gas that they heated it up and stopped it from cooling. In a way, the AGN stopped the cooling flow, which stopped the formation of stars in the IC and the areas around it. The X-ray glow we see now is caused by gas that should have fallen apart a long time ago, but is still floating in a hot, thin ring because of feedback from the galaxy's main engine. The X-rays can also be used to measure weight. Astronomers can figure out how heavy Abell 2029 is by looking at how the gas pressure balances gravity. The results back up what other tests have already said. The cluster is heavier than 500 trillion suns, and most of that weight is hidden in dark matter. The hot gas is only one part of this structure, but it shines the brightest, so we can see the unseen skeleton that holds the cluster together. The stripped satellites. The IC isn't the only one in the Abell 2029 cluster. A lot of smaller galaxies circle it, leaving behind faint streams of stars that look like the leftovers from a big cosmic meal. These are the stripped satellites, smaller friends that are being slowly broken up by the cluster's gravity and the IC's hunger. It's not so much that they are neighbors as that their identities are being taken away piece by piece. When a smaller galaxy ventures too close to the IC, it enters a region where tidal forces become overwhelming. The difference in gravity between its near side and far side stretches the galaxy, pulling stars loose. Over time, this process leaves behind delicate tidal tails and arcs that wrap around the giant. Many of these features are so faint they can only be seen in ultra-deep images, but they are unmistakable evidence of ongoing cannibalism. The satellites are literally being shredded alive, their stars donated to the endless halo of the Titan. But the IC isn't the only predator. The intra-cluster medium, the hot plasma filling Abell 2029, plays its own role in stripping satellites. As smaller galaxies plow through this medium, the pressure from the gas acts like a wind, blowing away their own cold gas reservoirs. This process, known as ram pressure stripping, leaves galaxies gas poor long before they even reach the IC. By the time they fall into the central giant, they are already shells, stripped of the fuel needed to form stars. All that remains is their stellar skeleton, which the IC readily absorbs. In nearby groups like Virgo and Coma, where spiral galaxies leave long trails of gas behind them, scientists have seen this process happen in real time. The IC's huge halo and Abell 2029's smooth X-ray glow both point to the same process at work, even though Abell 2029 is farther away. Every satellite that is taken apart adds a few billion more stars to the IC's collection. This helps the big star grow while leaving behind strange trails in the cluster. Some satellites survive for a while, orbiting like moths circling a flame. But even they cannot last forever. Over billions of years, dynamical friction robs them of orbital energy, dragging them closer until they, too, are consumed. The larger ones may merge violently, their cores plunging straight into the IC's center, feeding its black hole. The smaller ones dissolve more gently, scattering their stars into the outer halo. Either way, their fate is the same: erasure. The stripped satellites also help explain the faint halo problem. Every arc and plume of stars drifting in the IC's outskirts is a remnant of a satellite being dismantled. Over time, these features blend into the diffuse halo, extending it farther and farther. The reason the IC's halo stretches millions of light years is because it has cannibalized so many satellites that their debris clouds now overlap into one massive envelope. These stripped companions may also carry clues about the chemical history of the cluster. Each galaxy has its own mix of elements, forged in its stars and supernovae. When the IC absorbs them, their chemical fingerprints are preserved in globular clusters and halo stars. By studying these elements, astronomers can trace where the stars came from and reconstruct the meal history of the Titan. In this way, the stripped satellites act as breadcrumbs, telling the story of billions of years of cosmic dining. There's a tragic beauty to these galaxies. Imagine a once proud spiral, full of star-forming gas and glowing arms, falling toward the cluster's core. At first, it only feels the gentle tug of the IC. Then its gas begins to peel away, glowing faintly in ultraviolet as it is shocked by the cluster medium. Its arms distort, stars spilling into streams. Slowly, its identity dissolves, until all that remains is a faint smear of light in the halo of a much larger galaxy. To us, that light is barely detectable. To the galaxy, it is the end of individuality. A satellite might not even get to the IC before it is stripped bare by the cluster itself. These stars that were ripped from their homes move around the cluster without a purpose, mixing with the light that comes from inside the cluster. They are not actually inside the IC, but their end is the same. They will be forgotten in the light of something bigger. The satellites that have been stripped are not only victims of Titan, but also of everything around it. The missing spiral arms. Most people think of the Milky Way or Andromeda as galaxies because of their beautiful spiral shapes. These galaxies have long arms with bright blue stars and glowing clouds of gas. But the IC doesn't have any of that. Even if you use a lens, you won't be able to see any pinwheeling arms or beautiful patterns. Instead, you see a circle of light that is smooth and has no edges. The IC is an elliptical galaxy, which means it doesn't have any spiral arms. The absence of spiral structure is one of the defining differences between ellipticals and spirals. Spiral arms are sustained by a delicate balance, rotation, and density waves. As stars and gas orbit in a disk, they crowd into spiral-shaped regions, triggering star formation that makes the arms stand out. But in ellipticals like the IC, there is no disk. Stars move in random directions, like bees in a hive rather than cars on a highway. Without ordered rotation, there can be no spiral arms. How does a galaxy lose its arms? The answer lies in mergers. Spirals are fragile. When two collide, their delicate disks are shredded by gravity. Stars are flung into random orbits. Gas clouds crash and heat up, and the orderly pattern dissolves into chaos. Over time, the result relaxes into a smooth, elliptical shape. The IC didn't just lose its spiral arms once, it lost them thousands of times, each merger erasing structure until nothing remained but a golden haze. The missing spiral arms are also a sign of the IC's age. Spiral arms are places of ongoing star formation, lit up by massive young stars that shine blue and die quickly. In the IC, star formation has long since stopped. Without new stars to highlight patterns, any arms that once existed would have faded into obscurity. The galaxy's light is now dominated by older, yellow and red stars that blend into uniform brightness. The absence of arms isn't just about structure. It's about the end of stellar youth. The lack of spiral arms makes the IC appear deceptively boring in images. Compared to colorful spirals, ellipticals can look like dull smudges. But this simplicity hides complexity. The smooth glow is the result of billions of years of violent activity. Every merger that destroyed a spiral also built the giant we see today. The missing arms are a clue that the IC's beauty lies not in shape, but in scale and history. There's also physics at play. Spiral galaxies depend on angular momentum, the tendency of rotating systems to flatten into disks. But ellipticals have lost much of that ordered spin. The IC, being the largest of them all, rotates so slowly that any trace of a disk is gone. Its stars move in every direction, creating a pressure-supported structure rather than a rotation-supported one. Without that spin, spiral arms are impossible. It's very different from the Milky Way. The spiral arms of our galaxy are full of gas and dust that make new stars every year. They are nurseries that are always changing the way the galaxy looks. The IC, on the other hand, is clean. Its lack of arms shows that it is no longer active, with no cold gas, new stars, or patterns. What we see is the final product of galactic evolution, stripped of the features that make spirals shine. This transformation is not unique to the IC. Many galaxies in clusters lose their arms over time, especially when subjected to repeated collisions and the harsh environment of hot plasma. In fact, this is likely the future of the Milky Way. In about 4 billion years, when it merges with Andromeda, their spiral arms will tangle and dissolve. The end result will be a giant elliptical, glowing smoothly in yellow light, much like the IC. Looking at the IC is like looking into our own galaxy's destiny. The lack of spiral arms also makes the IC easier to study from an outside point of view. Arms, bars, and dust lanes make brightness patterns in spirals more complicated. Ellipticals, on the other hand, are smooth, which let scientists model their light with mathematical accuracy. The IC's structure almost exactly matches these patterns. This is a classic example of how galaxies relax after merging many times. Tidal streams around the Titan. The IC is not as perfect as it seems at first glance, no matter how smooth it is. It only takes a close look to see tiny scars. These are the tides, the gentle rivers of stars that circle the galaxy, the quiet signs of meals that are still being broken down. If the IC is the universe's biggest galaxy eater, then these streams are the food scraps it left behind. Tidal streams form when smaller galaxies are pulled apart by a larger one's gravity. As the victim falls inward, stars on the near side feel a stronger pull than stars on the far side. This difference stretches the galaxy, pulling stars into long, curved trails. To us, those trails look like faint arcs or shells of light wrapping around the predator. They are fragile, glowing only faintly against the darkness, and they fade with time as the stars disperse. But catch them in the act, and you see the story of cannibalism written across the sky. In the IC, these streams are especially telling. They show that even now, billions of years after its main growth, the Titan is still feeding. Smaller companions continue to spiral inward, torn apart as they approach the center. Some streams loop like ribbons, others arc like claws, and together they form a halo of shredded galaxies. Each one is a galaxy's death certificate, signed in starlight. Detecting tidal streams at the IC's distance is no easy task. The galaxy is over 1 billion light-years away, and its streams are billions of times fainter than the night sky. Astronomers use ultra-deep imaging, sometimes stacking exposures for dozens of hours, to pull these ghostly features into view. In recent years, telescopes have revealed arcs and shells extending for hundreds of thousands of light-years, faint outlines that betray the IC's ongoing appetite. The presence of streams also helps solve a mystery: how the IC's halo became so enormous. It's not just the product of ancient collisions. It's being built continuously, one satellite at a time. Every stream we see today is future halo light, destined to blend into the galaxy's diffuse envelope. In a way, the halo is the graveyard, and the streams are the funeral processions, slowly delivering stars to their final resting place. Tidal streams also act as forensic evidence. By measuring their shapes and motions, astronomers can reconstruct the orbits of the galaxies that created them. This allows scientists to work backward, piecing together the IC's meal history. Some streams reveal small dwarf galaxies, others point to larger victims. In every case, the message is the same. The IC is still growing, and it has been doing so for more than 12 billion years. On a smaller scale, these processes look a lot alike, which is strange. We can see tidal streams from dwarf galaxies like the Sagittarius dwarf galaxy, which is currently breaking apart, in our own Milky Way. These streams move across the sky like faint rivers in space. When you multiply that process by thousands of times, you get the IC, which is a very big version of the same story that spans millions of light years. Tidal streams also highlight the fragility of galaxies. Spirals and dwarfs may look robust, but when confronted with a gravitational giant like the IC, they are powerless. Their carefully arranged structures, arms, disks, bars, are pulled to pieces. In the end, they lose not only their stars, but also their identities. Once their streams fade into the halo, nothing remains to show they ever existed. The Titan does not just eat galaxies, it erases them from history. On a smaller scale, these processes look a lot alike, which is strange. We can see tidal streams from dwarf galaxies like the Sagittarius dwarf galaxy, which is currently breaking apart, in our own Milky Way. These streams move across the sky like faint rivers in space. When you multiply that process by thousands of times, you get the IC, which is a very big version of the same story that spans millions of light years. The age of the IC. The IC is not only very big, it is also very old. Experts say it started to form more than 12 billion years ago, which is only a few billion years after the Big Bang. That makes it almost as old as the start of time. The IC was building the huge, gigantic galaxy we see today, while our Milky Way was still in its early stages, slowly coming together from smaller proto-galaxies. We know this from the ages of its stars. When astronomers study the light from the IC, they find that most of its stars are old, more than 10 billion years. Their chemical composition also reveals their age. Early in the universe, stars formed mostly from hydrogen and helium, with few heavier elements. These so-called metal-poor stars dominate the IC's glow, meaning much of its population was born when the cosmos was still young and raw. This tells us an important thing. The IC must have formed during a time when stars were forming quickly, galaxies were smashing into each other a lot, and black holes grew quickly. In the first few billion years, when things were very unstable, the IC probably went through a number of huge mergers. Each one made it bigger and caused bursts of star formation. The IC was already well on its way to becoming the biggest galaxy when the universe was only a third of its present age. The IC is captivating, though, because of how it has aged compared to others. A lot of galaxies kept making stars for billions of years, but the IC stopped early. Its black hole and cluster surroundings stopped new stars from forming a long time ago, leaving behind a group of old stars. This is why it has a golden glow instead of the blue glow of a young galaxy. In the grand scheme of things, the IC retired early and did nothing for billions of years while other stars were still forming. The age of the IC also connects to its role in the Abell 2029 cluster. Being the central galaxy of a massive cluster requires time. Smaller galaxies had to fall inward, collide, and merge repeatedly, a process that takes billions of years. The fact that the IC sits so perfectly at the cluster's center today suggests it has been anchored there for eons, shaping the cluster as much as the cluster shaped it. Younger galaxies simply haven't had enough time to reach that level of dominance. The smoothness of its structure is another sign that it is very old. When galaxies that have recently merged show signs of trouble, like disks that are warped, cores that aren't centered, or light profiles that aren't straight. The IC, on the other hand, looks calm, with a level of brightness that can only come from being still for billions of years. Its dim ring still shows signs of recent meals, but the galaxy as a whole looks like it's grown up. Gravity has had time to heal from the bad times it went through as a child. The IC's age also shows how much the world has changed since it was created. Cosmos was smaller, thicker, and more linked when it first came together. Galaxy collisions happened a lot, and there was a lot of gas. Today, dark energy controls the universe. It is growing so quickly that galaxies in faraway groups will soon be unable to reach each other. There was a time in space when the IC could grow. Even if it had started later, it would never have grown to the size it is now. The IC isn't just old in this way. It's a product of its time, a holdover from a time when giants could still be made. Scientists can learn more about what will happen to galaxies in the long run by studying galaxies like the IC. For example, even though the Milky Way is about 13.6 billion years old, stars are still being made in it. When it joins Andromeda in 4 billion years, it will start to change into a huge ellipse. The IC and other galaxies are studied to find out what the future will be like. Because it is so old, it is both a reminder of the past and a look into the future. Why it's so rare. The universe doesn't give physicists many extremes, but they love them when they do. Not only is the IC the biggest galaxy we know of, it's also one of the strangest. You almost never see galaxies this big outside of the centers of rich clusters. And even in those places, not many are as big as the IC. That this giant is so rare helps us understand not only how it formed, but also why galaxies like the Milky Way are the norm and not the exception. The first reason is simple: environment. The IC lives at the center of Abell 2029, one of the densest clusters in the universe. Smaller clusters and isolated galaxies simply don't have the raw material to build something so big. You need thousands of galaxies packed into a gravitational well, orbiting, colliding, and merging over billions of years. Without that environment, a galaxy like the IC could never exist. The Milky Way, by contrast, resides in a relatively small group with only a few dozen members. That difference in neighborhood is why our galaxy will never reach the IC's scale. The second reason is timing. The IC began forming early, over 12 billion years ago, when the universe was denser and collisions were more frequent. That gave it a head start, allowing it to grow rapidly while smaller galaxies were still finding their shape. Today, conditions are very different. The universe is expanding faster and faster because of dark energy. Galaxies are moving apart, reducing the chances of large-scale mergers. Giants like the IC are relics of a cosmic era that no longer exists. New ones simply can't form in the present-day universe. Another reason lies in probability. Galaxy growth depends on a series of lucky events: timely mergers, plentiful gas, and a stable position at the cluster's center. Most galaxies don't experience all these conditions. Many fall into clusters too late, or are ejected before they can merge. Others remain on the outskirts, where they contribute to the cluster but never become dominant. The IC is rare because it had the perfect combination: early formation, central location, and enough time to consume thousands of companions. It's not just big, it's the cosmic equivalent of winning the lottery billions of times in a row. Even among brightest cluster galaxies, BCGs, the IC is exceptional. Most BCGs are only a few 100,000 light-years across, with star counts in the hundreds of billions. The IC, at 6 million light-years and over 1 trillion stars, pushes the boundaries of what a galaxy can be. This is why some astronomers debate whether it should even be considered a single galaxy, or whether it is more like a hybrid object, the luminous core of an entire cluster masquerading as one system. That ambiguity underscores its rarity. It sits at the blurry line between galaxy and cluster, a scale few other objects approach. Rarity also comes from fragility. Galaxies can grow large, but they can also be destroyed. Major cluster mergers can disrupt central giants, scattering their stars and preventing smooth growth. The fact that Abell 2029 is unusually relaxed and stable may be the reason the IC was able to reach its current size. In more chaotic clusters, giants are less likely to survive intact. Once again, the IC was lucky, forming in a place where its growth was not violently interrupted. The rarity of giants like the IC has profound implications for cosmology. In computer simulations of galaxy formation, objects of this scale appear only occasionally and always in the most massive clusters. Their abundance, or lack of it, helps test theories of dark matter and cosmic structure. If we found many more galaxies like the IC, it would challenge current models. The fact that we've found so few confirms that the universe behaves as expected. Giants are possible, but only in exceptional circumstances. The endgame of galactic evolution. Not only is the IC the biggest galaxy we know of, but it may also be the last step of galactic development. When you look at it, you can see what happens when the universe lets gravity play for billions of years straight. It shows the end game, when new stars stop forming and structures are smoothed out by mergers. At that point, a galaxy is less of a city of stars and more of a region of light. In many ways, the IC answers a central question in astronomy. What happens to galaxies after countless collisions? Spirals like the Milky Way are still in their prime, actively forming stars, rich with gas, and decorated with spiral arms. But when spirals merge, their disks are destroyed, their gas is consumed or expelled, and they settle into ellipticals. Over billions of years, ellipticals at the centers of clusters continue to grow, devouring everything that falls their way. The more they eat, the bigger they become, until they reach a stage where growth slows to a crawl. The IC is the clearest example of this final stage. It is a fossil galaxy, built not from steady star formation, but from the remains of thousands of others. Its 6 million light-year halo is a graveyard of mergers. Its trillion stars, the survivors of long-ago spirals and dwarfs. Its golden color speaks of age, its depleted core of black holes scouring, its faint streams of light of meal still underway. Everything about the IC screams completion. It has reached a size that few galaxies will ever approach, and in doing so, it shows us the destiny of cluster cores. Scientists who study the universe often say that it's like cosmic cannibalism gone too far. The center galaxies of smaller clusters may still expand quickly, consuming their companions at a rapid rate. But in a big, calm cluster like Abell 2029, the main giant has already used up most of what it can. The other galaxies are either too small, too far away, or have been stripped of their parts by the intracluster medium. Growth keeps going, but it's not fast. There is still food for the IC, but it is no longer a feast. That great time of growth is over. This is why many astronomers see the IC as a preview of the cosmic future. Our own local group, for instance, will eventually merge into a single giant galaxy when the Milky Way collides with Andromeda 4 billion years from now. That remnant, sometimes nicknamed Milkdromeda, will resemble a giant elliptical. Over tens of billions of years, it will consume smaller companions like the Magellanic Clouds and M33. Eventually, it will become the central giant of its own local cluster, glowing red and quiescent, much like the IC today. Studying the IC is like peering into a time machine, giving us a glimpse of our home galaxy's eventual fate. The endgame of galactic evolution is also shaped by dark energy. As the universe expands faster, distant galaxies move away too quickly to ever merge. That means the IC, and others like it, are nearing the end of their growth. They have become as large as they are likely to get, frozen in place by the accelerating cosmos. In the far future, the IC will sit in an increasingly empty sky, its cluster companions gradually drifting beyond the observable horizon. What remains will be a single massive galaxy, aging quietly in the dark. The fate of its stars is equally somber. With no new stars forming, the IC's trillion suns will age and die. The brightest giants will go supernova, leaving behind neutron stars and black holes. The more numerous smaller stars will slowly fade into white dwarfs, then into cold remnants called black dwarfs. Over trillions of years, the galaxy will dim, its golden glow replaced by darkness. The IC's endgame is not just about structure, it is about entropy. The fire of star formation will never return. The fossil record of cannibalism. The IC has been through many crashes with other galaxies, but its smooth golden glow hides the signs of those meals. If you look very closely, you can see that the galaxy has patterns frozen in stars that show how it grew into the biggest galaxy ever found over a long period of time and through a lot of violence. When two galaxies merge, the violence leaves scars. Stars are flung into arcs and shells, globular clusters are scattered, and faint ripples of light ripple outward. Over billions of years, many of these features fade, blending into the smooth profile of the new galaxy. But some remain. In the IC, astronomers have detected subtle structures, shell-like distributions of stars and faint stellar envelopes that hint at the devouring of smaller galaxies long ago. These shells act like tree rings, each one marking the time of a past collision. The fossil record also exists in the globular clusters orbiting the IC. These dense star clusters are remarkably resilient, surviving events that tear entire galaxies apart. By analyzing their ages and chemical compositions, astronomers can trace where they came from. Some clusters are metal poor, showing they originated in primitive dwarfs consumed early in the IC's history. Others are more metal-rich, pointing to larger spiral galaxies devoured later. Together, they form a timeline, a galactic autopsy report etched in the orbits of star clusters. The stars around the IC are another sign. These tiny stars are spread out over millions of light-years and are not in the center of the galaxy. Instead, they circle in a way that shows they were once part of other galaxies. Their movements are shaky, and their chemistry is varied, which is exactly what you'd expect from a group of people that got together by eating each other. Every one of them is a fossil, a piece of a galaxy that no longer exists. The smoothness of the IC might make it seem as if all traces of cannibalism are gone, but that's misleading. The uniform light we see is the result of relaxation, gravity smoothing out chaos over billions of years. Yet just beneath that calm surface, deep imaging reveals faint tidal streams still winding through the outskirts. These streams are fragile fossils, temporary records that will eventually fade. For now, they serve as direct proof that the IC is still consuming satellites even today. There's also evidence locked in the core depletion mystery. The galaxy's unusually empty central regions point to repeated black hole mergers. Every time the IC swallowed another massive galaxy, its central black hole paired with the newcomers. Their dance flung stars outward, hollowing the core. That depletion is itself a fossil record, an absence that testifies to collisions that can no longer be seen. The missing stars are the ghosts of ancient galaxies, erased but still remembered in the gap they left behind. This record of fossils is being studied for more than just academic reasons. Astronomers use it to figure out how the universe's biggest structures are put together. Scientists can test models of galaxy growth by putting together pieces of the IC's history of eating other stars. Simulations show that the largest cluster galaxies should grow by merging with other galaxies rather than steadily making new stars. It is clear that this theory is correct because of the IC's rings, groups, and tidal streams. Its fossil record shows that giants are put together, not made. What's striking is how this process repeats across scales. In the Milky Way, we see the same fossil record in the Sagittarius stream, the Gaia Enceladus remnant, and other structures that betray past collisions. The IC simply takes this process to the extreme. Where our galaxy has devoured a handful of dwarfs, the IC has consumed thousands of galaxies, each one leaving behind some trace. The difference is not in kind, but in scale. From a human perspective, the idea that galaxies can leave fossils might sound strange. We think of fossils as bones buried in rock, but in astronomy, fossils are patterns of light and motion, chemical fingerprints, and missing stars. They are records not of animals, but of entire galaxies erased by gravity. The IC is both the predator and the museum, preserving in its structure the story of cosmic cannibalism on the largest scale. Its role in Abell 2029's gravity well. To understand the IC, you need to know about the Abell 2029 cluster, where it lives. Over 1 billion light-years away, this huge structure is made up of thousands of galaxies, trillions of stars, and a huge ocean of hot plasma that is held together by dark matter. The IC, which holds the whole cluster together, is at the very center of this huge system. It is an important part of Abell 2029's gravity well and can't be left out. Galaxy clusters are the most massive bound objects in the universe. Their gravity is so strong that they act as giant wells, pulling everything inside into orbits that can last billions of years. But while dark matter provides most of that gravity, it is the central galaxy that serves as the visible heart. In Abell 2029, the IC plays this role better than almost any other galaxy in the universe. It isn't just sitting at the bottom of the well, it helps define where the bottom is. The stars, galaxies, and gas in Abell 2029 move under the combined pull of dark matter and the IC's vast mass. Smaller galaxies orbit around it like moons around a planet. The intracluster gas, heated to tens of millions of degrees, settles into a smooth, spherical shape, centered on the IC. Even the faint intracluster light, the scattered glow of orphaned stars, appears brightest near the IC, as though acknowledging the giant as the cluster's ruler. What makes the IC unique is just how much of the cluster's light it provides. In many clusters, the brightest cluster galaxy, BCG, accounts for perhaps 10 to 20% of the total starlight. In Abell 2029, the IC dominates far more. Its trillion stars produce a significant fraction of the cluster's luminosity, making it the undisputed heavyweight in the region. This overwhelming brightness is why astronomers sometimes describe it as not just a galaxy, but as the central core of the cluster itself. The influence extends beyond light. The IC's supermassive black hole, weighing tens of billions of suns, has likely shaped the cluster's history. When active, it blasted out jets that pushed aside hot gas, regulating how the cluster cooled. Without that feedback, the gas might have collapsed into new galaxies. Instead, Abell 2029 is dominated by a single monster, with smaller galaxies stripped and sterilized long before they could grow. The IC isn't just a passenger in the cluster, it's a regulator controlling the balance of heat and growth in its environment. Another role the IC plays is as a gravitational beacon. When astronomers map the motions of galaxies in Abell 2029, they find that the IC sits precisely at the cluster's center of mass. Everything else orbits around it, from massive ellipticals to tiny dwarfs. If the IC weren't there, the cluster would still exist, but its structure would be far less stable. The galaxy acts like a weight at the bottom of a spinning bowl, keeping everything else in balance. This gravitational role also makes the IC an important cosmological tool. By measuring how galaxies move relative to the IC, astronomers can calculate the cluster's total mass. By studying how its halo blends into the intracluster light, they can test theories of dark matter distribution. The IC is not just a galaxy, it's a marker, a natural test particle in one of the universe's largest laboratories. This is a rare role that you should know about. A center galaxy isn't nearly as important in many groups. Some have more than one giant fighting for the core. Others are not relaxed, and their centers are not in the same place as the largest galaxies. Abell 2029 is unique because it is so orderly and is controlled by a single giant. The IC is not only big, it is also properly placed at the very bottom of a well that is so deep that it connects hundreds of galaxies. It would be easy to tell who is in charge if you could see the cluster for yourself. Smaller galaxies would circle the IC like sparks around a fire, making it look like a fire in the middle. The X-rays would make the hot plasma glow silently. It would stay in place thanks to the gravity of the IC and its dark matter ring. Every particle and star would be pulled toward the giant at the center of the system, making it feel like it's bending in. Black hole feedback. A black hole tens of billions of times the mass of the Sun lies at the middle of the IC. But this monster didn't just grow in the dark and be quiet. It once decided the fate of the whole galaxy and even the cluster around it. The key is in a process scientists call black hole feedback. This is when a black hole feeds and changes everything around it with its energy. In the IC, that feedback may have been the key that stopped the formation of stars and turned the galaxy into the huge thing it is now. When gas falls toward a black hole, it doesn't vanish instantly. It forms an accretion disk, swirling faster and faster, heating to millions of degrees. Magnetic fields and pressure launch jets of material at nearly the speed of light. Radiation floods outward across the spectrum, from radio waves to X-rays. For a galaxy the size of the IC, the energy output of these events dwarfed everything else, sometimes exceeding the combined luminosity of every star in the system. That energy doesn't just escape into space, it slams into the surrounding gas, heating it and driving it outward. In clusters like Abell 2029, where galaxies sit in a thick atmosphere of hot plasma, this feedback has dramatic consequences. Without it, the gas should cool over time, condensing into clouds that collapse into new stars. But in the IC, the black hole's outbursts kept the gas hot, preventing cooling flows. The result, star formation was quenched on a galactic scale. Evidence for this feedback is written across Abell 2029 in X-ray cavities, giant bubbles carved into the hot intracluster medium. These cavities, detected by telescopes like Chandra, align with faint radio emissions, suggesting they were inflated by black hole jets millions of years ago. By calculating the energy needed to carve them, astronomers conclude that the IC's black hole once released more power than millions of supernovae combined. That feedback not only shut down star formation inside the IC, but also affected the cluster's gas, altering its entire environment. This feedback cycle is now understood as a self-regulating system. When gas cools and flows inward, it fuels the black hole, triggering an outburst. The outburst then reheats or ejects the gas, starving the black hole of fuel. Activity ceases until more gas cools, and the cycle begins again. For the IC, these cycles likely repeated many times in its past, each one reinforcing its transition into a red and dead giant. Today, the black hole appears dormant, but the scars of past activity remain etched into the plasma sea around it. What makes the IC extraordinary is the scale of this process. In the Milky Way, our black hole occasionally flares, but its influence is modest. In the IC, feedback occurred on cluster-wide scales, regulating not just one galaxy, but thousands. Its outbursts likely prevented Abell 2029's central gas from cooling into dozens of new galaxies. In this sense, the IC's black hole was not only a destroyer, but also a sculptor, deciding the architecture of the cluster itself. Feedback could also explain why the IC's core is running low. Stars were spread out as black holes joined and blasts shook the center. The feedback and gravity scouring made the center areas look surprisingly empty. This is another sign that the black hole's effects aren't just on gas that can't be seen. They also affect stars that can be seen. New studies of how galaxies change over time support this picture. Without input from black holes, big galaxies in models keep making stars, making them too bright and blue compared to what we see. The models can only make galaxies like the IC, huge, smooth, and quenched when input is added. That means the IC is not just a strange event, but also an important piece of proof showing how important black holes are to the growth of the universe. To get an idea of how big feedback is, think of jets shooting out from the IC's black hole that are hundreds of thousands of light years long, glowing with radio waves, and making holes in plasma that is 1,000,000 degrees Fahrenheit. Those jets could move galaxies through them like dust motes move through a storm. Those bursts kept the IC from sinking under its own gas for billions of years. The Titan was held back by its hunger. The giant's rotation. You might picture swirls spinning smoothly and arms sweeping like cosmic pinwheels when you think of galaxies. At our location, the Milky Way spins at about 210 kilometers per second, and it makes a full turn every 225 million years. Part of what makes circles so interesting is how they spin. The IC is not like that though. The giant doesn't spin very much, given how big and heavy it is. This slow spin is a hallmark of elliptical galaxies. Unlike spirals, where rotation organizes gas and stars into neat disks, ellipticals are dominated by random motion. Stars move in every direction, not in a coordinated spin, but in a swarm. It's as if the galaxy is a hive of bees, buzzing chaotically rather than flowing like cars on a racetrack. In the IC, this random motion dominates so strongly that any residual rotation is almost irrelevant compared to the galaxy's internal velocity dispersion. Why is the IC so slow to rotate? The answer lies in its history of mergers. Every time a spiral galaxy merges, its ordered rotation is disrupted. The angular momentum is scrambled, and stars are tossed into new orbits. After enough collisions, any memory of a disk is erased. In the IC's case, which has swallowed thousands of galaxies over billions of years, all traces of coherent rotation have been destroyed. The result is a galaxy supported not by spin, but by the collective random energy of its stars. Analysts use spectral lines from the IC's light to figure this out. The light from stars moves a little when they move toward or away from us. This is called the Doppler effect. Scientists can tell if the galaxy spins like a wheel or buzzes like a swarm by making a map of these changes across it. For the IC, the trend is clear: the least amount of spin and the most dispersion. It's the perfect example of a system that is backed by pressure. This lack of spin has consequences. Without rotation to flatten it, the IC is not a thin disk, but a broad, rounded structure. Its 6 million light-year halo spreads in every direction, shaped more like a sphere than a pancake. That's one reason it looks so smooth in images. Spirals need spin to maintain their arms. The IC needs only gravity to hold its swarm of stars in place. The slow rotation also affects the galaxy's stability. In spirals, disks can be fragile, warped by encounters or instabilities. The IC's pressure-supported structure is more robust. Its stars move in random orbits, making the whole system less vulnerable to being disrupted by collisions. Ironically, the very chaos of its stellar motions creates long-term stability. That stability is part of why the IC has remained so dominant at the cluster's core. There's another consequence. The lack of spin helps explain why the IC no longer forms stars. In spirals, rotation compresses gas into arms, creating the density waves that trigger star formation. Without spin, gas in the IC simply floats, heated by the cluster environment and black hole feedback. No compression means no new stars, reinforcing the galaxy's red and dead status. Comparisons highlight just how different the IC is from our own Milky Way. Our galaxy is relatively modest in size but rich in rotation, which drives its structure and fuels ongoing star formation. The IC, by contrast, traded spin for mass. By devouring thousands of galaxies, it gained bulk but lost order. It is a giant not because it spins, but because it is absorbed. Simulations of galaxy evolution show that this is the natural endgame of mergers. When two spirals collide, their spins often cancel out, depending on their orientation. Repeat this process enough times, and the net rotation dwindles to almost nothing. For the IC, which has merged more than perhaps any other galaxy, the result is nearly complete rotational silence. Comparison to the Milky Way. Scientists often say that the IC is like our own galaxy when they talk about it. We know what the Milky Way is and can use it as a guide. But when you put them next to each other, the difference is almost silly. The IC is so much bigger than the Milky Way that it makes our galaxy look like a small town in comparison. Start with size. The Milky Way is about 100,000 light-years across, a number that feels enormous until you put it next to the IC's 6 million light-years. That makes the IC at least 60 times wider. If you placed the IC where the Milky Way is, its edges would extend far past Andromeda, past Triangulum, and out to the very edge of the local group. Every galaxy we call neighbor would be swallowed whole. Now consider stars. The Milky Way hosts somewhere between 200 and 400 billion stars. The IC, by contrast, contains more than 1 trillion, possibly 2 trillion. That's the equivalent of 10,000 Milky Ways worth of stars packed into one system. If the Milky Way is a city of stars, the IC is a continent. Its stellar population is so massive that it accounts for a significant portion of the total light of its entire cluster. And then there's the central black hole. Sagittarius, a star, at the heart of the Milky Way, weighs about 4 million suns. That sounds impressive until you compare it to the IC's central beast, which may weigh 40 billion suns. The difference is mind-boggling. If Sagittarius, a star, is a mountain, the IC's black hole is Everest stacked on Everest, a monster that could swallow our black hole without noticing. Even their colors tell different stories. The Milky Way shines with a mixture of blue and yellow light. Blue from young stars in its spiral arms, yellow from older stars in its bulge. It is alive, forming 1 or 2 new stars every year. The IC, by contrast, glows golden and uniform, the color of age. Its star formation has been quenched for billions of years. No spiral arms, no nebula, no bright star nurseries. Where the Milky Way is a thriving city, the IC is a vast, quiet graveyard. The shapes of the two galaxies also couldn't be more different. The Milky Way is a spiral galaxy with orderly rotation shaping a disk and arms. The IC is an elliptical galaxy, supported not by spin but by the random motions of its stars. Where our stars flow in an elegant band across the sky, the IC's stars would swarm in all directions, their motions chaotic and unpredictable. Living in the IC would mean a sky without order, just a diffuse haze of countless suns. The halos of the two galaxies highlight the difference further. The Milky Way's stellar halo extends a few 100,000 light-years, containing ancient stars and globular clusters. The IC's halo stretches for millions of light-years, filled with the debris of thousands of galaxies it has consumed. The Milky Way has a modest collection of globular clusters, maybe 150. The IC likely has hundreds of millions, each one a fossil from a galaxy it devoured. There is a big difference between them, even where they are. The Milky Way is in the local group, which is made up of only a few dozen galaxies and is pretty quiet. The only real star that is close by is Andromeda, which it will join with in a very long time. The IC, on the other hand, is in the middle of Abell 2029, a group of thousands of galaxies and a huge amount of hot gas. The Milky Way is a part of a small community. The IC is like the ruler of a big city. The parallel that might be the most humble comes from how obvious it is. What if you could put the Milky Way next to the IC? It would blend into the glow. The trillion suns on Titan would block out the Milky Way's light, making it look like a candle dancing next to a campfire. Even Andromeda, which is bigger than the Milky Way, is not even close to the IC in terms of size. Galaxies it has likely eaten. People sometimes call the IC the Galaxy Eater, which is a fair name. It must have eaten a huge number of its neighbors to get to where it is now, 6 million light-years across and home to more than 1 trillion stars. Simulations show that the IC has probably eaten thousands of galaxies the size of the Milky Way, as well as many smaller galaxies and irregulars. Every dim star in its halo is a leftover from a cosmic meal, proof of the people it has eaten over billions of years. When astronomers run computer models of galaxy clusters, they see a clear pattern. The central galaxy grows by stripping and merging with smaller members, its mass snowballing over time. By scaling these models to the IC's observed size and brightness, researchers estimate that it has consumed at least 1,000 to 2,000 Milky Way-sized galaxies, and possibly far more if you include smaller ones. That staggering number is necessary to explain its vast halo and trillion-star population. But what did these galaxies look like before they were devoured? Many were probably spirals, rich in gas and dust, glowing with blue stars and bright nebulae. Others were smaller ellipticals and dwarfs, quieter but still full of ancient stars. Each one had its own history, its own structure, and perhaps even planetary systems with life. In the IC's maw, all of that individuality was erased. Spirals lost their arms, dwarfs were torn apart, and their stars were scattered into the Titan's endless halo. Evidence of this feeding frenzy is still visible. Deep images show faint tidal streams and shells looping around the IC, remnants of galaxies that were shredded but not yet fully blended in. Globular clusters, those dense swarms of stars, are another clue. The IC contains hundreds of millions of them, far more than any normal galaxy. Many of these clusters likely came from swallowed galaxies, preserved as fossils even as their parent systems were destroyed. By studying the chemical fingerprints of these clusters, astronomers can trace the diversity of the IC's meals. Some metal-poor, some metal-rich, some ancient, some relatively young. The fact that the IC's core is running low is another piece of secondary proof. Its strangely hollow center points to repeated mergers of supermassive black holes, which happen when galaxies with black holes at their centers crash into each other. They throw stars outward every time they swirl together, making the galaxy's heart. For the IC's core to be this empty, there must have been dozens or even hundreds of these kinds of collisions, with each one consuming another galaxy. The sheer number of victims also helps explain the IC's dark matter halo. Every galaxy carries its own invisible cocoon of dark matter. When the IC swallowed them, their halos merged into one, creating the massive gravitational envelope that now holds its stars and gas. This accumulation of dark matter is as much a record of cannibalism as the stars themselves, a silent framework built from the ghosts of galaxies long gone. From a human perspective, the thought is staggering. Imagine the Milky Way, with its 200 billion stars, swallowed whole. Multiply that by 1,000, and you begin to grasp what the IC has likely consumed. Every galaxy devoured was once a universe of its own, with billions of stars and potentially billions of planets. Now they are anonymous points of light in a giant's body, their histories erased by gravity. And the process isn't over. Even today, smaller galaxies in Abell 2029 are being stripped and absorbed. Their gas is torn away by the cluster medium, their stars smeared into streams, their identities dissolved into the IC's halo. Over the next billions of years, the Titan will continue to feed, though at a slower pace as dark energy stretches the universe and isolates clusters. Eventually, it may double its current mass, incorporating almost every galaxy in Abell 2029. There is also a cosmic irony in this. Even though the IC has eaten thousands of galaxies, it hasn't made many new stars in billions of years. Its growth does not come from birth, but from being used up. It doesn't really make new stars. Instead, it recycles old ones and stops new ones from forming. The people it kills don't go away completely. They live on as part of its glow, but they lose everything that made them special. The smoothness paradox. You might think that the IC looks confused after all the things it has been through. Thousands of mergers, billions of stars being thrown into new orbits, and galaxies being eaten by other galaxies. You could picture streams of stars that are jagged, clumps of light, or structures that are warped from all the crashes. But it doesn't look like the IC is a mess at all. It seems smooth. Its brightness level slowly decreases from the middle to the edges, and there are no visible bumps or scars. This is the smoothness paradox. How can a war-torn world look so peaceful? The paradox begins with mergers themselves. When two galaxies collide, the process is messy. Stars are thrown into tidal tails, gas clouds crash and ignite, and shapes warp dramatically. We see this in closer galaxies like the antennae, where two spirals are in the process of merging. Their shapes are twisted and jagged, filled with streams of torn-out stars. If the IC has experienced thousands of such collisions, why doesn't it look like a tangled wreck? The answer lies in time and gravity. After a merger, chaos dominates for hundreds of millions of years. But gravity is a patient sculptor. Over billions of years, the random motions of stars average out, tidal tails fade into the background, and the galaxy relaxes into a smooth equilibrium. The result is the featureless light profile we see in ellipticals. The IC has had more than 12 billion years of this process. Its smoothness is not the absence of violence, but the erasure of its scars. Experts have a very good way of measuring how smooth this is. In order to show how the galaxy's light fades from the center outward, they use surface brightness maps. It is almost perfect for the IC because the shape fits statistical models called Circic functions. That means the way the light is spread out is reliable. There are no bumps that would show clumps or new problems. As a drawing, it seems like one of the most organized galaxies ever looked at. But we know that its past is anything but ordered. This is the essence of the paradox. How can a galaxy that has eaten thousands of others look more regular than galaxies that have experienced far fewer mergers? The best explanation is scale. In smaller galaxies, a single merger can leave noticeable scars. In the IC, the sheer number of collisions averages out the chaos. Like paint blended on a canvas, the individual strokes vanish into a uniform shade. The more violent its history, the smoother it becomes. That doesn't mean there are no traces at all. With ultra-deep imaging, astronomers have detected faint tidal streams and arcs in the IC's outskirts. These features are fragile and will fade with time, but for now they reveal that cannibalism is still ongoing. The paradox is not that the IC has no scars, but that its overall structure looks far too clean for its past. Gravity has covered the wounds with a mask of uniform light. Simulations help explain why. When galaxies merge, their stars don't collide directly. They pass through one another, since the distances between stars are so vast. Instead, it's gravity that reshuffles their orbits. Over time, these orbits settle into new distributions, spreading out smoothly. Gas and dust, meanwhile, are either consumed, expelled, or heated until they no longer form clumps. The result is a system that looks calm, even though it was built from chaos. The IC is the ultimate demonstration of this process. The smoothness paradox also raises philosophical questions about what galaxies really are. Are they snapshots of violence or averages over time? In the IC, we see both. Its smooth profile hides the fact that every star was once part of a smaller structure. Its present calm is built from past chaos. It is, in essence, a lie of light, an illusion of serenity born from unimaginable destruction. For astronomers, this paradox is useful. The very fact that the IC looks smooth allows its light to be modeled precisely, helping researchers calculate its size, brightness, and mass with confidence. At the same time, the faint deviations from smoothness, its streams and shells, offer glimpses into its violent past. By comparing the two, scientists can reconstruct both the history and the present of the largest galaxy in the universe. Gravitational lensing potential. There are times when light doesn't move in straight lines. Gravity changes its path when it gets close to something very heavy. The name for this effect, which Einstein's theory of general relativity predicts, is gravitational lensing. With its huge size and weight, the IC is almost the perfect natural lens. It has such a strong pull on the universe that it can bend the light of galaxies far away, making them bigger and more splotchy across the sky. At first glance, lensing might sound abstract, but it's one of the most powerful tools in modern astronomy. By observing how light from background galaxies is bent, astronomers can map the mass distribution of the lensing object, even the invisible dark matter. For the IC, sitting at the center of Abell 2029, this is crucial. The galaxy isn't just massive, it's embedded in a dark matter halo weighing as much as a quadrillion suns. That invisible halo is what gives it such extraordinary lensing power. There are two kinds of gravitational lensing at play here: strong lensing and weak lensing. Strong lensing creates dramatic arcs and multiple images of the same background galaxy. Weak lensing, on the other hand, produces subtle distortions, stretching background galaxies just slightly. In clusters like Abell 2029, both occur. The IC, with its overwhelming gravitational field, is at the center of it all. It doesn't just act as a galaxy, it acts as a telescope, bending the universe behind it into view. They have used lensing around systems like the IC to look at galaxies that are billions of light-years away and would not be visible otherwise. Galaxies in front of Titan are being eaten, but galaxies behind Titan are also being shown. Its weight makes it like a magnifying glass, letting us see into the past of the universe. With the help of gravity lenses in huge clusters, some of the farthest galaxies ever seen were found. Abell 2029 isn't the most well-known lensing cluster, but it is one of the most powerful because of how big it is. Lensing helps prove that the IC has a dark matter ring, which is very intriguing. Astronomers only find a small amount of the mass needed to explain the lensing effects when they measure the stars and gas that can be seen. Dark matter must be where the rest of it comes from. Scientists can figure out what the unseen halo looks like by making maps of the shapes of background galaxies seen through Abell 2029. The end result is a ghostly map that shows exactly where we think the IC's gravity will be strongest. The IC is not only a galaxy, but also a part of a bigger web, which can be seen through lensing. Its gravity field joins with that of Abell 2029's cluster ring to make a lens that is so strong that it can make things billions of light-years away look smaller. In this way, the IC doesn't act by itself. Working together with its cluster, they bend space itself. A deep picture shows smooth lines of skewed galaxies. This shows that the IC is inside one of the universe's deepest gravity wells. This means that the IC is both a study and a tool for scientists. We can figure out how heavy the galaxy is, map its ring, and test cosmic models by looking at how it bends light. But lensing also lets us see past it, like a cosmic microscope, thanks to its mass. But the Titan is more than just a monster. It's also a view into galaxies from the very beginning of the universe. Imagine standing in a spacecraft near the IC, looking outward. The background galaxies would appear warped, stretched into arcs that curve around the Titan. Some might even appear duplicated, their light split into multiple paths. To the human eye, it would be eerie, as though space itself were bending. But to astronomers, those distortions are data, proof that mass bends light, and that the eye see's mass is almost beyond comprehension. The color magnitude diagram anomaly. People who study galaxies often use the color magnitude diagram, CMD, which is easy to use but very useful. To find out how old and hot the stars are, it sets a galaxy's color against how bright it is, its magnitude. Most galaxies can be easily put into one of two groups. There are spirals and irregulars in the blue cloud, as well as new blue stars. On the red line are elliptical galaxies and older galaxies that are full of red and yellow stars. The green valley is in the middle, and it's where galaxies change as their star formation stops. By all accounts, the IC should sit comfortably in the red sequence. It is massive, elliptical, quenched, and glowing with ancient yellow stars. And yet, when astronomers measure its position on the CMD, something strange happens. The IC doesn't quite fit. It is brighter and redder than almost any galaxy on record, lying beyond the typical bounds of the red sequence. This is the color magnitude anomaly of the IC. The reason is partly its sheer size. Most red sequence galaxies, even the largest, contain a few 100 billion stars. The IC contains 1 trillion or more. That pushes its magnitude far above the norm. On top of that, its stellar population is unusually old and metal-poor, making it even redder than expected. Together, these traits push the IC off the standard chart, placing it in what some astronomers jokingly call the Red Desert, a region of the CMD where almost no other galaxies exist. This anomaly challenges our understanding of how the red sequence works. The sequence itself is thought to be the end product of quenching. As galaxies stop forming new stars, their color shifts from blue to red, and their brightness depends on how many stars they already had. But the IC is so extreme that it may not be just another data point. It may be a category of its own. It suggests that the normal rules of galactic evolution break down at the highest masses. The IC may have had more strong input than other ellipticals, which could be one reason. It's possible that the galaxy's center black hole stopped star formation so completely that it turned redder than any model could have predicted. Another reason is that its huge halo is made up of a lot of faint metal-poor stars that were separated from dwarfs. Because these stars are older and redder than most, they make the galaxy's color lean even more toward red. In this way, the IC's strange behavior is not a mistake. It's a sign of its past of eating other things. There's also the issue of scale. The CMD was designed to classify normal galaxies, but the IC may be so large it breaks the framework. When you add thousands of mergers together, you don't just shift along the red sequence. You overshoot it entirely. That overshoot creates an outlier, a galaxy that technically belongs but doesn't fit. In a way, the IC is the CMD's exception that proves the rule. This strange event is both annoying and exciting for scientists. It makes neat models of how galaxies evolve harder to understand, but it also gives us a one-of-a-kind place to work. Scientists can improve their ideas about how galaxies grow, cool down, and age by looking into why the IC is off the chart. It might even show us small things we don't fully understand yet, like the part of stars inside clusters, or how the effects of repeated black hole feedback add up over time. The anomaly also matters for cosmology. Large surveys like the Sloan Digital Sky Survey, SDSS, rely on CMD classifications to study galaxy populations across the universe. Outliers like the IC are rare, but they remind us that the universe doesn't always follow our categories. Nature doesn't care about neat diagrams. It produces monsters that bend the rules, and those monsters teach us where our models need to evolve. A peek into the future of galaxy clusters. The IC isn't just a thing from the past, it's also a look into the future. A lot of the time, astronomers see more than a cluster giant when they look at this huge galaxy. They think it shows what will happen to our local group and all galaxy groups in the future as the universe gets older. In this way, The IC is like a time machine because it shows us where the development of the galaxy will end up. Right now, our Milky Way is still a vibrant spiral, actively forming stars. Andromeda, our nearest neighbor, is much the same. But in about 4 billion years, the two will collide. Their disks will tangle, their gas will ignite bursts of star formation, and eventually their spiral arms will dissolve into a single elliptical. Astronomers sometimes call this future galaxy Milkdromeda. Though it won't be anywhere near as massive as the IC, it will still be far larger than either of its parents. Fast forward tens of billions of years, and the local group itself will evolve into something resembling Abell 2029. All the smaller galaxies, Triangulum, the Magellanic Clouds, and dozens of dwarfs will eventually merge with the Milky Way Andromeda remnant. Over time, the local group will collapse into a single giant galaxy surrounded by a faint halo of stripped stars. This is exactly the kind of process that built the IC. In other words, when we look at it today, we are seeing our own fate, billions of years ahead of schedule. The IC tells us about more than just our local group, though. It also hints at what will happen to galaxy groups in the long run. Clusters grew quickly in the early universe because of a dense web of strands in space. It happened a lot, and as it did, galaxies built bigger and bigger systems. But now that growth is slowing down. The universe is expanding faster because of dark energy. This is pulling clusters apart and cutting them off from new galaxies. Each cluster will turn into a closed island, cut off from the rest of the universe, in the very far future. Inside those islands, central giants like the IC will continue to grow by consuming nearby galaxies. But eventually, even that will stop. Once all the smaller members are eaten or stripped, the central giant will dominate and the cluster will stabilize. At that point, the cluster will look much like Abell 2029 does today, a smooth ball of hot plasma anchored by one overwhelming galaxy. The IC shows us that this endgame isn't just theoretical, it's already real, visible through our telescopes. This future is scary. In 100 billion years, the universe will have grown so big that groups far away will be too far away to see. Local groups, like the one that has the IC in it, will be the only ones that can be seen. For the people who live in that future, the night sky will be empty except for their own cluster. It will look like the universe is smaller, quieter, and more empty. As an example of this, the IC is a giant that already rules its own area while the rest of the universe fades away. It also teaches you about size. Many galaxies are about the same size as the Milky Way, but it seems very big to us. Seeing the IC makes you understand that as galaxies evolve, they make things that are much bigger than we can imagine. All around us, the forces that will bring the Milky Way and Andromeda together are already at work. It was just that the IC had more time, more friends, and a bigger gravitational well to draw from. Its future is a bigger version of ours. In this way, studying the IC is like looking at both a space rock and a crystal ball at the same time. It tells us about the past and how galaxies met, grew, and died. But it also shows us what's to come. Spirals that are bright and active will slowly turn into giants that are quiet. The variety of the universe will fade into a uniform golden light. And eventually, a few large ellipticals will dominate every cluster. For astronomers, this is both comforting and unsettling. Comforting because it confirms that the universe follows patterns we can understand. Unsettling because those patterns end in silence. The IC has already reached that stage, glowing softly with the afterlight of 1 trillion stars, no longer making new ones. It is the endgame of clusters, a glimpse of what the cosmos will look like when growth ceases and time stretches on. The largest known galaxy debate. Researchers always add a caveat when they say that the IC is the biggest galaxy in the universe. Maybe. The title of largest galaxy is surprisingly hard to give, given how big and well known it is. That's because it's not easy to measure galaxies. And there are other players in the cosmic list who each have their own claims. This has led to a discussion that is still going on. The IC is usually in the lead, but they do have opponents. How do you decide where a galaxy ends? Unlike planets or stars, galaxies don't have solid surfaces. Their brightness fades gradually into space, blending into halos and intra-cluster light. Do you stop counting at the faintest detectable stars, at a certain brightness threshold, or where the galaxy's gravity ceases to dominate? Depending on the choice, the measured size can change dramatically. The IC, with its faint halo stretching 6 million light-years, illustrates this perfectly. That number comes from tracing light profiles out to extremely faint levels, but some astronomers argue that much of that light belongs not to the galaxy itself, but to the surrounding cluster. If you include all the diffuse light, the IC is the king. If you cut it shorter, the crown becomes less certain. Alcyoneus, a huge radio galaxy found in 2022, is one of its main rivals. In stars, Alcyoneus is not especially huge like the IC. Its center galaxy isn't very special, but it sends out radio waves that reach over 16 million light-years, making it the biggest object ever found that is connected to a single galaxy. When it comes to size, Alcyoneus has the most radio lobes, but if stars are important, the IC is king. Another rival is ESO 146-IG005, a central galaxy in a cluster about 1.2 billion light-years away. Some measurements suggest its halo could stretch more than 7 million light-years, potentially exceeding the IC. However, the data are uncertain, and the definition of its edge is even fuzzier than for the IC. Until deeper imaging confirms it, the IC remains the better established giant. Then there are galaxies like M87 at the center of the Virgo cluster. Though smaller in diameter, around 1 million light-years, it contains a black hole comparable in mass to the ICs, and its influence dominates the Virgo cluster. Some astronomers argue that dominance, not diameter, should define the largest galaxy. By that measure, M87 deserves more attention. But in terms of sheer size and star count, it falls short of the IC. This debate reveals a deeper truth. Galaxies don't fit neatly into categories. Nature doesn't care about our labels. Central cluster galaxies blur the line between galaxy and cluster core, their halos mixing with intra-cluster stars. Radio galaxies blur the line between stellar systems and jets that extend far beyond them. Even the term largest depends on whether we're measuring stars' halos or influence. The IC's case is still strong. It has a halo that is 6 million light-years across, a population of 1 trillion stars, and the most stars of any galaxy known to science. This makes it the most likely choice for the title of biggest known galaxy in terms of stars and stellar mass. Its competitors either use strange meanings, like radio jets, or data that isn't very reliable. The IC wears the crown until something else is proven beyond a doubt. But the debate isn't just about bragging rights. It has scientific importance. By identifying and studying these extremes, astronomers test the limits of galaxy formation models. If galaxies like the IC or ESO 146-IG005 are more common than we think, it could mean our theories underestimate how efficiently clusters build giants. If they are truly rare, it confirms that the universe produces outliers only in very specific conditions. Either way, the search refines our understanding. There's also a philosophical lesson. Humans like to rank things, the biggest, the brightest, the farthest. But in the cosmos, absolutes are slippery. Galaxies don't come with neat borders or single measurements. They fade, blend, and sprawl. What looks like a clean number is really a decision about where to draw a line in the dark. The largest galaxy debate isn't a failure of astronomy. It's a reminder of how messy and wondrous the universe really is. The invisible gas halo. Even though the view is mostly made up of the IC's trillion stars, stars are not the only thing that makes up this galaxy. There is an unseen gas cloud around it that is just as important but much harder to see. This structure can only be seen in radio and X-ray waves, not visible light like the faint glow of stars in its outer ring. It's a cage of hydrogen, helium, and hot plasma that covers millions of light-years. The atmosphere is so big that it makes the ring around the Milky Way look like a small pool next to the ocean. The presence of this halo was uncovered with radio telescopes tuned to the 21-centimeter line of neutral hydrogen. Although the IC is largely quenched and forms no new stars, faint signals revealed a sprawling hydrogen reservoir spread thinly across its outer regions. The gas is so diffuse it doesn't collapse into stars, but it still orbits as part of the galaxy's structure. More detailed studies showed that this gas halo merges seamlessly with the intracluster medium of Abell 2029, making it difficult to tell where the galaxy ends and the cluster begins. The picture got even better with the help of X-ray telescopes. Hot plasma at tens of millions of degrees was found around the IC by instruments like Chandra and XMM Newton. This plasma only shines in X-rays, so we can't see it. However, it makes up a huge part of the galaxy's overall baryonic matter. Most of the IC's normal matter isn't even in stars. It's in this huge, unseen halo of gas. This is what scientists find when they add up the masses of stars, gas, and plasma. Why is the gas invisible in visible light? The answer is both temperature and density. Cold gas, like that in the Milky Way's disk, clumps into clouds that shine with emission lines and form new stars. But in the IC, the gas has been heated to extreme temperatures, either by cluster collisions or by feedback from its supermassive black hole. At those energies, the atoms are stripped of electrons, and the gas glows only in high-energy radiation. To optical telescopes, it disappears. To X-ray and radio telescopes, it blazes. This halo helps explain another mystery: why the IC has stopped forming stars. Despite having trillions of solar masses of gas available, most of it is too hot and diffuse to cool and collapse. Instead of feeding new star nurseries, the gas lingers in limbo, trapped in the galaxy's and cluster's gravity. It is fuel the galaxy can no longer use, a pantry full of food locked away behind an unbreakable door. The invisible halo also deepens the dark matter puzzle. The motions of gas in the outskirts show that it is bound by a gravitational envelope far more massive than the stars alone can account for. This reinforces the idea that the IC's dark matter halo is one of the largest ever measured. The gas acts as a tracer, mapping the contours of that invisible skeleton. Without it, we would have far less certainty about the galaxy's true size and mass. The gas halo isn't entirely featureless. Deep imaging has revealed faint ripples and asymmetries in the X-ray glow, hints of disturbances left behind by mergers or ancient black hole outbursts. These ripples are fossil records of violence, just like the tidal streams of stars. They suggest that the gas halo is still settling, still responding to past upheavals, even as the stars appear smooth and calm. Comparisons to the Milky Way are staggering. Our galaxy's halo of gas extends maybe a few 100,000 light-years, containing enough hydrogen to form a few billion stars. The IC's halo stretches millions of light-years and contains hundreds of times more gas, though most of it will never form stars again. The scale difference is so extreme that the IC's gas halo could swallow our entire local group and still have space left over. The invisible halo might seem irrelevant. After all, we can't see it with our eyes. But for astronomers, it's crucial. It tells the story of the IC's quenching, its mergers, and its relationship with Abell 2029. It shows how galaxies and clusters are not separate objects, but parts of a continuous web of matter. It reminds us that what we see in visible light, the stars, is only a fraction of reality. If you could see through the IC like you could see through X-rays, the view would be amazing. In the middle of this huge, sparkling bubble of plasma, the golden glow of the stars would fade into the dark of space. The real edge of the galaxy is that unseen halo, which goes farther than any optical picture shows. It is like the IC's secret spine. It holds 1 trillion stars together in a cage of gas and dark matter. The loneliness of giants! The IC is the biggest galaxy we know of. It's a giant made up of trillions of stars that have joined together to form one big galaxy. Even though it is so big, it feels strangely lonely. One of the most interesting things about giant ellipticals is that they are dead, even though they have more stars than almost any other system in the universe. Most of the lights have already gone out in the IC, so it's not a city full of life and stars. The loneliness begins with its quenched state. The IC no longer forms new stars. The gas that once fueled brilliant nebulae and clusters has been stripped, heated, or blown away. Without blue giants, without spiral arms, the galaxy has no ongoing creation. What remains are old, dim stars quietly burning through their fuel. They shine, but they do not renew. It is a galaxy where the birth rate has fallen to nearly zero. For a system this vast, the silence is deafening. Then there is the matter of companions. The IC lives in the dense environment of Abell 2029, but as the central galaxy, it has already consumed many of its neighbors. The satellites that remain are being stripped or slowly dragged inward, destined to disappear into the Titan's halo. Over billions of years, the IC has eliminated competition. It has become so dominant that it stands virtually alone, the emperor of a cluster where no other galaxy comes close to rivaling its size. Dominance has brought isolation. Even its stars tell a story of loneliness. Most are ancient, older than 10 billion years. They orbit in random paths, far apart in the enormous halo. In the Milky Way, a night sky on a habitable world is filled with the glow of spiral arms. In the IC, the view would be emptier, its stars spread so thin across millions of light years that even within the largest galaxy ever found, the sky might look sparse. 1 trillion suns, yet vast stretches of darkness between them. This loneliness is not unique to the IC. Other brightest cluster galaxies, BCGs, share the same fate. They are overwhelmingly massive, but also overwhelmingly dead. They have size without vitality, light without youth. It is as if growing too large comes at the cost of vibrancy. Galaxies that eat too much become victims of their own success, bloated giants left to drift in quiet. The IC is simply the most extreme case, a galaxy that ate so many companions it left itself with no one left to grow with. Theorists often say that this is the end of the development of the galaxy. Spirals like the Milky Way are still making stars, building structure, and making different kinds of life. Some big bands, like the IC, have already made it to the end, though. They don't change much anymore, just fade away slowly. In a world that used to grow all the time, they are warnings that everything gets old and lonely with age. The loneliness also extends into the future. Because of dark energy, the universe's expansion is accelerating. Over time, galaxies outside Abell 2029 will slip beyond the cosmic horizon, unreachable forever. Billions of years from now, the IC and its cluster will be isolated, cut off from the rest of the universe. No new galaxies will arrive to feed it. No fresh light will fall into its halo. It will rule, but over a shrinking kingdom. The Titan will be alone, not just in its cluster, but in the cosmos itself. There is a kind of tragic poetry in this. The IC is the ultimate product of cosmic cannibalism, but in feeding on others, it created its own solitude. The very process that made it the largest galaxy in the universe also condemned it to loneliness. It shines today with the combined light of 1 trillion stars, but that light is fading. In the far future, its stars will dim into white dwarfs and black dwarfs, leaving only darkness. End of its growth. Without stopping for billions of years, the IC grew. Any galaxy that got too close was stripped, eaten, and sucked into its huge ring. Being able to eat each other is what made it the biggest galaxy ever found. Now, though, the feast is ending. Like the world, the IC is moving into a new phase where growth has pretty much stopped. The primary culprit is dark energy, the mysterious force accelerating the expansion of the universe. In the past, galaxies were closer together and collisions were inevitable. But as the cosmos stretches, galaxies move farther apart and fewer are drawn into the gravitational grasp of giants like the IC. Even in a rich cluster like Abell 2029, the pace of mergers has slowed. The easy meals are gone. The surviving galaxies are either too far away or already stripped of their most valuable material. Inside the cluster, the IC will still consume a few satellites over the next billions of years. Ram pressure stripping and dynamical friction guarantee that smaller galaxies spiraling inward will eventually vanish into its halo, but these mergers will be relatively minor. The days of devouring the Milky Way-sized galaxies are long past. What remains is cleanup, not conquest. The IC is no longer a growing predator, but a bloated giant digesting its final scraps. Researchers can see this change in the way it cools down. It is no longer making new stars because its gas has been burned up, blown away, or used up. The huge amounts of hydrogen that used to help it grow are now stuck in a hot, spread-out sphere and can't cool down. It doesn't matter how many more galaxies fall in, they won't add much new gas. Most of them are stripped of their data by the surroundings of the cluster before they get to the core. In other words, there is nothing in the IC's kitchen, and no order is coming. The faint halo problem highlights this end stage. The galaxy's outskirts are already swollen with stars spread across millions of light years. Adding more material won't change its character. It will simply smear the halo further, diluting the light into invisibility. The structure is already so large that new additions hardly register. Growth, in any meaningful sense, has ended. The black hole in the middle is another thing to think about. When it was active, it sent out jets that controlled how stars formed. Even though it is sleeping, it still has power. Any gas that dares to come in risks being heated up or pushed out before it can settle. Because of black hole feedback, even if new fuel got to the center, it would probably go to waste. The Titan is stuck in a loop that won't let it grow. This end of growth is not unique to the IC. It is the fate of all massive galaxies in clusters. Once they reach a certain size, they stop changing in any dramatic way. Instead, they simply fade. Their stars age, their gas stays hot, and their halos stabilize. The universe shifts from a time of creation to a time of decline. The IC is just the most dramatic example, a preview of what every central cluster giant will eventually become. The future of the IC is therefore not expansion, but isolation. As dark energy continues to accelerate cosmic expansion, galaxies outside Abell 2029 will drift beyond the observable universe. The IC will remain bound to its cluster, but beyond that, the sky will grow empty. In 100 billion years, the Titan may rule an island universe, cut off from all others. Its trillion stars will still glow, but no new ones will replace them. Its reign will be eternal, but its kingdom will be shrinking. The galaxy that ate the universe's past. The IC is bigger than any other galaxy we've found. It's a memorial to the past of the universe, a building that remembers almost everything that came before it. You can see not only a galaxy when you look at the IC, but also the pieces of thousands of other galaxies. In a real way, the galaxy ate the past of the universe. Every star in the IC was once part of something else, a spiral with glowing arms, a dwarf floating quietly at the edge of the cluster, a galaxy with its own black hole and its own story. Over 12 billion years, the IC consumed them all. Their shapes are gone, their identities erased, but their stars remain, glowing in the Titan's halo. The faint golden light we see today is not the light of one galaxy. It is the combined light of an entire history of galaxies, merged into one. This makes the IC not just a galaxy, but a cosmic archive. Its shells, its tidal streams, its globular clusters, all of them are fossils, records of ancient collisions. Astronomers study their chemical signatures and motions to reconstruct the galaxy's past, like archaeologists sifting through ruins. Every trace of metal-rich stars hints at a spiral once devoured. Every faint shell of stars reveals the outline of a dwarf galaxy torn apart. Piece by piece, the story comes together. The IC is not a single creation, but an assembly, a monument built from the bones of the universe's past. The Titan's black hole tells the same story. It is not the product of a single collapse, but of countless mergers, each one adding mass as galaxies combined. Its tens of billions of solar mass weight is proof of how many black holes have spiraled together in its core. Each merger erased another galaxy, but also preserved its central darkness inside the IC's heart. The black hole is not just a singular monster, it is a collection of every monster the galaxy has ever eaten. Even its color magnitude anomaly is a record of history. The IC is redder and brighter than almost any other galaxy because it has aged so thoroughly. Its stars are old, its gas exhausted, its youth long gone. That extreme position on the diagram is not an accident. It is the signature of billions of years of eating, quenching, and aging. It is the universe's past, distilled into one giant point of light. There's irony in this. When the IC ate its neighbors, it took away their personality, but by doing that, it kept them alive in a different way. Those galaxies still have bright stars. They just shine because they are a part of something bigger that you can't miss. The IC has mixed the different parts of a cluster's history into one unity. It's a golden glow that doesn't show the life of one galaxy, but the deaths of 1,000 galaxies. The IC is not only a wonder to scientists, it is also a warning. It shows us what happens when nothing stops the world from going in its own direction. When galaxies clash, join and get bigger, only the biggest ones are left. The making of stars stops. The spirals fade. Diversity goes away. The young, exciting world grows old and quiet. The interstellar cloud, IC, is a fossil that shines billions of light years away and shows us that nothing can escape time. For people, the size is shocking. The IC was very old when Earth was formed 4.5 billion years ago. Before there was life, before animals, before people looked up at the stars, the IC had already eaten most of its neighbors. Its story is not similar to ours. It is much longer and goes back almost to the beginning of time. To study it is to touch the universe's deep past and see in one thing the memory of billions of years that we can hardly imagine. IC 1101 is more than a galaxy. It's a cosmic monument built from everything it consumed. 1 trillion stars, thousands of galaxies, and billions of years of history now fused into one golden haze. It shows us the universe's hunger, its violence, and its silence. And in its immensity, it also shows us our future, because one day the Milky Way will meet the same fate. The Galaxy Eater is not just the largest galaxy we've ever found. It's a reminder that in the end, gravity always wins. If you enjoyed this journey into the deepest corners of the cosmos, please subscribe, like, and comment to Beyond Horizons. Your support helps us keep exploring the universe's greatest mysteries.